everybody. Welcome to the Astronomy Festival organized by the Tucson Amateur Astronomy Association. I'm Terry Lappin. I'm our outreach coordinator for most of our big outreach projects. Also joining us today is May Smith. She's our president, and Jim Knoll. He is our Star Party manager. We usually do an in-person event at Brandy Fenton Park, but due to COVID, unfortunately, we're doing a virtual event. Now, I say unfortunately, but actually the virtual events can go all over the world. So we actually are getting a wider audience. So it's not such a bad thing. It's just we don't have the person-to-person interactions. I hope you join us for the rest of the afternoon and into the evening when we'll be doing some astronomy observing through telescopes. We've got the sun observing during the day, and then as sun sets, we'll switch to the nighttime viewing with the telescopes, looking at deep sky stuff. All of our events are being streamed on both Facebook and YouTube. Links will be available on both of those places to get to the events, the activities. We also have TAAA members on the chat and the comments watching for your questions. That will be live, and we will respond to your questions as they come in. Okay. We do want to know where you're watching from. So put in the comments and in the chat what city, state, even part of Tucson. If you're in the southwest part of Tucson or whatever, let us know where you're at. We like to keep track of how far out we're reaching or how close we're reaching. I'm now going to introduce May, our president.
Welcome to our Tucson Amateur Astronomy Association Astronomy Festival that is virtual this year. We have a lot of TAAA dedicated members working to provide a fun and interactive experience for you over the next several hours. Special thanks to both Terry and Jim and our TAAA volunteers for putting on this virtual event. We hope you can join us for all the Astronomy Festival events or for the portions that most interest you. The recordings will be available to view later if you can't watch it all today. Enjoy the activities, and if you have follow-up questions, contact us through our website at tucsonastronomy.org.
Thank you, May. Now I'll introduce Jim Knoll. He's our Star Party manager. Jim?
Thanks, Terry. So as both Terry and May said, we do hope that you enjoy our Astronomy Festival. Throughout the event, we're going to have, as Terry mentioned, we're going to have some solar observing of the sun. We're going to actually have some activities about the solar system, the universe, galaxies, all kinds of fun stuff. And then later on, we'll also do what's called a walk around the night sky. So it'll be normally in person, we would do that with a laser pointer and point out different things in the night sky. But what we'll do this time is we'll use a planetarium program to highlight different areas within the night sky that are kind of cool to look at, and then also talk about both Native American lore and ancient star lore. And then we'll wrap up with an evening star party later on. Hopefully next year, we'll be back in person with the Astronomy Festival. We've had some pretty good experience doing virtual events throughout the last year. So we'll probably keep doing some virtual events, but the festival itself is much better in person. So with that in mind, please enjoy the festival. Next up is going to be some solar observing.
Thank you, Jim. Also, I wanted to mention that also on our social media sites, Facebook and YouTube, we've got lots of other activities from previous events, previous star parties that you can watch. So check out our social links. Thank you very much.
All right, welcome everyone. I'm Jim Knoll with the Tucson Amateur Astronomy Association. And now we're going to kind of kick off our program with some solar observing. So we're going to take a look at the sun through a couple of different telescopes, and it'll be in a couple of different formats. One will be in white light, where we can hopefully see a few sunspots. And then the other one will be in hydrogen alpha, and we'll be able to look at some of the activity that's going on around the sun. Now, after we get done with this first part of the solar observing, we will we'll have some toolkit demonstrations on additional topics of astronomy, one of which will be on the sun. So we'll go into greater detail in between the episodes. And then we're going to, after we get done with that, a little bit later on, we're going to have another solar session of observing the sun using the hydrogen alpha telescope, so that you can kind of compare and contrast between the two different views. Now, the sun is obviously the dominant object in our solar system. The sun all by itself makes up 99.8% of all the matter in our solar system. Out of the little 0.2% that's left over, Jupiter makes up 0.1% of that. And then all the other planets, the asteroids, the comets, everything else makes up the last 0.1. So that just says that the sun is huge. Now, the sun itself is not necessarily a large star. It's a medium-sized star. So there's a lot of stars that are larger than the sun, and there's a lot that are smaller than the sun. But we're a medium-sized sun. Sun's been around for about 4.5 billion years, so it's about halfway through its life. So it's got a long ways to go yet. And it goes through an 11-year cycle, which I'm going to explain when I do the magnetic sun activity here in just a minute. The sun is about 870,000 miles across, and you can put 1 million Earths inside the sphere of the sun. So that's how big it is. All right, and with me today right now is Bernie Stinger. Bernie's going to show a picture of his telescope and talk a little bit about his setup, and then he will show us what he's got on the telescope. Over to you, Bernie.
Thank you, Jim. This afternoon, we're going to be looking at the sun in a couple of different formats, as Jim mentioned, white light and hydrogen alpha. Now, to do that requires two separate telescopes. So out in front of my home, I currently have two separate telescopes set up, and I can alternate between them. So we'll be able to see what each of them is showing individually. So I'm going to show you a picture to begin with of my two telescopes. There's the two telescopes in front of my home. The one on the left is a celestron telescope, and in front of it, you can just make it out. It's kind of a round looking big disc, is a white light filter. So this is the type of filter that most people with small telescopes that maybe came with a filter, maybe it didn't, maybe you bought one extra. This is the type of filter that most likely would come with most telescopes, and it's called a white light filter. Now, to the right is another telescope. This one is a Lunt hydrogen alpha telescope. And this telescope is designed specifically to look at the light of hydrogen alpha. So they're both pointed at the sun, but different kinds of telescopes. And we'll get into the difference between them once we start looking. So to start with, let's take a look at what the white light telescope should look like. This is the live image of what the white light telescope is looking at currently. And you can see why they call it a white light filter, because it makes the sun look like a big white disk. And it's also called a continuum filter because it's letting through pretty much all of the different wavelengths of light at the same time. Reds, greens, orange, blue, yellow, they're all coming through at the same time, creating a white image. And on the white light image, you can just make out one small little tiny sunspot. And if you haven't spotted it yet, I'm going to zoom in on it. It's right there, a little tiny one. And it's dancing around because we're looking through the sun's atmosphere. So it won't be a nice steady image constantly. It'll be a dance as the upper atmosphere kind of shifts the image around. But that tiny little spot is probably in the range of the size of the Earth. As Jim mentioned to you earlier, you can fit 1 million Earths into the sun. So with that in mind, you can tell that this tiny little spot, even though it's not very large, is about the size of the Earth in relationship to the size of the sun. I'm going to zoom back out again. You can see how small it is in comparison to the sun itself. Now, the sun rotates. The sun rotates just like the Earth rotates. The Earth rotates in 24 hours, as we all know. The sun rotates in about 25 days. So if there's a sunspot like this one on the sun, and you watch it day by day, it will slowly be in a different spot as the sun rotates. So each day it'll move about this far or so. So tomorrow it might be here, the next day it might be over here, the next day it might be over here, and so on, as the sun slowly rotates around. And sunspots don't last that long. They can last typically for days, but sometimes they're very short lived, and sometimes they actually last for weeks. And I remember seeing a couple sunspots a few years back that actually were visible the second time around. So they can last quite a long period of time if they're large enough and active enough. So that's what the white light picture looks like, the white light telescope. I'm going to shut that back down, and I want to shift over to what's called a hydrogen alpha telescope. So let me do that. Okay, the image you're seeing now is from the hydrogen alpha telescope. Now, hydrogen alpha, the reason they call it a hydrogen alpha is because of the frequency of light that the hydrogen alpha telescope is looking at. It's not looking at the whole spectrum of light from the sun. It's looking at a specific wavelength of light from the sun, which is around what's called 6,500 angstrom units. Now, don't let that bother you, what angstrom units are. Just think of it as a frequency of light that's in the red spectrum. So it will give the sun a reddish hue. by looking at that particular frequency of light, we can see things on the sun that a white light filter can't, because we're zeroing in on what's called the emission line of hydrogen. So very hot hydrogen emits very strongly at this frequency of light. And therefore we can see anything that's active with hydrogen on the surface and around the surface of the sun. So if we look at the screen up here, I'm going to bring my mouse up slowly. You'll notice two kind of white splotches on the surface of the sun. I'm going to zoom in so you can see them a little more clearly. This blotch, if you will, this white patchy area is actually that dark sunspot that we were looking at earlier. But in hydrogen alpha, it takes on a different color. The spot itself is right here, but you'll notice surrounding that spot are spot or patches that are brighter. Those are areas of the sun's surface that are actually hotter than the background of the sun. So that's why it's standing out as a bright area. Also, if you look at that section, other section there, there's actually another sunspot there, but it's too small to see in the white light filter. However, we can make it out in hydrogen alpha. Now, quite often these sunspots will have shape to them. You'll notice this one kind of has direction to these white patches. They kind of moving downwards and to the right. And the ones up here kind of moving upwards to the left. The reason for that is the magnetic field lines that are involved with these sunspots. Sunspots have tremendous magnetic fields, and that the gases that are coming off the surface of the sun, hydrogen gas, that gas is following those magnetic field lines. And that's why we're seeing direction to these patches. If we back off and look a little lower, you'll also notice down below, there's some areas of the sun. Here's one here down below it towards the bottom. It looks like a black streak. I think there was another one towards the top, and we can go up and take a look at that later on. These black streaks are flares, or what's called prominences, that are coming off the surface of the sun, and they look black or darker, I mean reddish, because they are cooler, slightly cooler than the surface itself. So they have a relatively darker appearance because of that. And I think there was another one towards the top. There was a patch up there as well. Yeah, up here. Here's another one that's just coming off, just coming around the limb. There's another big patch here that's probably a prominence that's rotated back onto the surface. It's so we can see it as a darker patch.
All right, so that was a kind of a really cool view of a different kind of telescope view of the sun. You know, a lot of people have the nighttime telescopes that you can use to look at the stars and objects in the night. And it's very simple and easy to get a white light filter that just goes on the end of the telescope. You just need, or make one, but you need to make sure that when you do that, you make it out of the correct material and make it very carefully, because looking at the sun without any kind of protection can damage your eyes big time. And if you look at it through a telescope without the proper filter on there, it can actually damage the optics of the telescope. So just like any other time, when you're looking at the sun, even without a telescope, you want to make sure you wear solar glasses that are made to look only at the sun. They should be black. When you look through them, when you're not looking at the sun, it should be black. And then when you look at them at the sun, you should see the round disk of the sun. But you also want to inspect them and make sure there's no tears or anything like that. Same thing goes with telescopes. So with the white light filter, you want to make sure that you've got a good filter that's protecting your eyes in the telescope. All right, so that was our review of white light. And in a short little while, we'll be back with some additional solar observing, and we'll be looking through Bernie's Hydrogen Alpha telescope.
All right, welcome everybody. So I'm Jim Knoll, and we're going to do a little activity to learn more about the sun. Now, we just did some solar observing this morning, or earlier, and we were looking at the sun in what we call white light with a solar filter to look at the sunspots on the surface of the sun. And later on in the program, we're going to switch to a hydrogen alpha telescope, and we're going to actually look at the hydrogen wavelength of the sun. So we're going to be able to see the activity that's going around the edge of the sun, like prominences and some of those kinds of things. And plus we'll be able to see actually what's going on the surface of the sun as well. So we'll look through an actual solar telescope later on. But in the meantime, I want to kind of talk a little bit about our star, our very special star, our sun. Now our sun is about 4.5 billion years old, so it's middle-aged. So it's still got a long ways to go. And it was born out of what we call a stellar nursery. So later on in the program, stick around because we're going to have a video on the Orion Nebula. You're going to actually be able to fly through the nebula. And the Orion Nebula is a stellar nursery. So what a stellar nursery basically is it's a large hydrogen gas cloud sitting out in space. And it just sits out there until something happens to kind of perturb it, just like those little dust bunnies under your bed, or when you rub your hands and they start getting hot, and frictions to kind of help things clump together. So what'll happen is that a star might pass through the nebula, or a supernova, which is a star that'll may explode nearby and agitate or stir up the nebula. And that will start the star forming process inside this nebula. Now these gas clouds are huge. You can get hundreds, if not sometimes thousands of stars made out of this one little gas cloud. Our sun, 4.5 billion years ago, was born out of a similar gas cloud to what the Orion Nebula is. So as that process happens and the material starts clumping together, what forms the protostar is what we call it. Eventually it'll get bigger and bigger and bigger, and gravity will take over, and it'll start pulling in more and more of the gas right around it. And it'll get large enough that it'll really start compressing down in the center of the protostar. And the core will get hot enough, about 15 million degrees, and guess what happens? It ignites, and it ignites as a star. And so what's happening now is that the star itself is made primarily out of hydrogen and helium. And so now that nuclear fusion that's taking place is converting hydrogen into helium. And what's left over, a little bit is left over, and that's the energy and the light that we see from the star. So as it gets bigger and bigger, the core will get hotter and hotter. Now, stars are different temperatures. Our sun, in the core of our sun, the temperature is 27 million degrees. So it got larger and larger and compressed more and more and ended up at a temperature of about 27 million degrees. So let's take a look inside the sun now. All right, so here's kind of a cutaway view of our sun. You'll see here's the core we were just talking about, and that's where it's 27 million degrees. as this photon of light and energy works its way out through the sun, out to the edge of the sun, it can take several 100,000 years or longer to get out to the edge. So it has to go through all this plasma. There's what's called a radiative zone, a convective zone, and then out here at the edge is the edge of the sun called the photosphere. That's the surface we see. The photon of light and energy I told you was about 27 million degrees in the center. As it works its way out, by the time it gets to the edge of the sun, it's about 10,000 degrees. And then once it gets to the edge of the sun, after several 100,000 years, it takes 8 minutes at the speed of light to get from the sun to your eyeballs or to feel the heat on the surface of your skin. So it comes very fast once it gets to the edge of the sun. There's another layer even above the photosphere called the chromosphere. And that's an area that the scientists are still studying because we're just really not sure what's going on with that. Now, anytime, and we didn't talk about this earlier, we probably did, we will during the solar observing portion, but anytime you're looking at the sun, you want to make sure that you wear solar glasses and make sure that they're approved solar glasses so that they're the ones that will really work on the sun, not sunglasses, but solar glasses. So ones like this, sometimes you can get an eclipse viewer card like this, and it should be black when you're not looking at the sun at all. But when you put it on the sun, you'll see just the disk of the sun. All right, so that's kind of the inside of the sun. Now let's take a look at the outside of the sun. This morning we looked at sunspots. Hopefully we saw some good sunspots on the surface of the sun. That's what they kind of look like here. They're just little black spots. Now, why do they show up black to us? That is because they're slightly cooler than the surrounding area of the sun. So I said earlier, the surface of the sun is about 10,000 degrees. The sunspots are about 8,000 degrees. So to our eyes, they show up black. Now, the sun goes through an 11-year cycle. So it starts off at what we call a solar minimum. And then in about 6.5 years, it kind of peaks out in activity. And it gets lots more activity in about 6.5 years. And that's where we're going to see lots more sunspot groups as it goes up. And then it'll go through a decline for another 6.5 years back down to a minimum again. So it's about 11 years between minimum and minimum, or max and max. We're about 1 year past the solar minimum. So we're climbing up towards the maximum. So it'll get more and more sunspots and prominences and other activity. Now, these sunspots also have another very important feature. When we look at the sun through the hydrogen alphascopes later today, you'll be able to see what looks like prominences, which is what we call prominences, and they look like little loops of gas coming off the edge of the sun. Now, the sun has a huge magnetic field all the way around it. And so what's happening is the plasma gas is coming out of the sun, looping up into space, and then is actually, when it loops up, it's following the magnetic field lines of the magnetic area and coming back down into the sun. So what happens is these magnetic field lines, called prominences, actually anchor themselves right on a sunspot group. So when we're looking at the sun this way, it's actually, you see the loop coming off, and that's what we call a prominence. If you look at the sun straight on, then all you see is the top of the prominence. And what's happening here, and what you're seeing is, you're seeing a line. So the prominence, you can't see the three-dimensional part of the prominence. And so what that's called a filament, and that's along the surface of the sun. And we should see those through the hydrogen alphascopes as well. And we'll see just little lines right on the surface of the sun. So prominences and filaments. Now, what happens when the energy of the sun gets really, really strong? These prominences with this plasma gas in this loop can get all twisted up as the magnetic field lines get twisted, because the sun rotates. And what happens is it'll get twisted up like this, and then it can actually break off of the sun. And when it breaks off of the sun, all this plasma gas goes out into space and gets caught up in the solar wind, and it can come towards Earth. When it breaks off of the sun, what we call this? We call this a solar flare, and it's got plasma gas in it, and it can get ejected towards the sun. If the flare or the activity is really, really strong and it's a huge storm, then we call it a coronal mass ejection, or a CME. And that's just lots and lots and lots of plasma gas coming off the sun out into space. Now the sun creates a huge wind off of it, and it blows way out to the outer solar system. So this material can come off the sun and fly right straight towards the Earth. And it takes about 2 days for it to get from the sun to the Earth. And while that's happening, because this material is plasma gas, so it's magnetically charged, so it's got a north pole and a south pole. And so scientists and astronomers are watching this gas as it comes towards this storm as it comes towards the Earth. And as they do that, they're going to look to see if they can determine what the poles are, which is the north pole and which is the south pole. Because guess what happens? We don't want that stuff to make it all the way down to Earth. Well, just like the sun has a huge magnetic field around it, the Earth has a magnetic field around it as well. Because in the center of the Earth, we have a molten iron core. And as the Earth spins, this molten core will spin as well. And it creates electricity, basically. And it creates a magnetic force field around the Earth. So as the plasma gas reaches the Earth, most of it gets pushed around the Earth and just flies out into the solar system. So that's a really important shield for us. But if it's a large enough event, what can happen is the material, the plasma gas can go around the sun, and then it might come in the back door. Whichever pole is pointed away from the sun, either it's north pole or south pole, the material can come down that pole and reach the Earth's atmosphere. And guess what? If you live in the northern states or Canada or Russia, and it's coming down the North Pole, you see what we call the northern lights, which are those lights that flicker across the sky. If you're on the South Pole, you see the southern lights. And that's the plasma gas interacting with the poles of the Earth. Now, if it's a big event like a coronal mass ejection, and there's a lot of plasma coming in, then guess what? It can affect the satellites that are in orbit around the Earth, because they're in the outer edge of our magnetosphere. And so the people watching the satellites may close them up, shut them down for a period of a day or two while this event processes. Or if it comes down the poles and reaches down into the Earth's atmosphere, it can affect our power grid and a lot of other things that are all magnetically based, electrically based. And so what can happen there is if we're not watching close enough, it could actually blow out all these huge transformers that are part of our power grid. So the people watching the power grid may actually shut down the power grid in the area where the storm is going to be the worst. And what that'll do is they'll isolate these huge transformers so that as the storm hits, it won't affect them. So the power would be down for a couple of days maybe, instead of months or even a year, while they have to replace these transformers, these huge transformers that are really, we don't have a lot of them. So there's a real dynamic interaction between the sun and the Earth. The sun helps facilitate life. It gives us heat, it gives us energy, but it can also have some aspects that are not so good for the Earth. And all those things have to take into effect when we do space travel as well. When we go to the moon, we're outside the Earth's magnetosphere. When we go to Mars, we're outside the protective Earth. So we have to watch that very closely and try to protect our astronauts the best we can. So anyway, that's a little bit more about the sun, the insides of the sun. Stay tuned later on. We'll look at the sun in hydrogen alpha, and we'll see how active it is. Hopefully we'll have some good prominences coming off, and then we'll go from there. Thank you. How long was that?
Hi, everybody. This is Terry Lappin. I hope you're enjoying our event today. I am here to talk to you about astronomers and how they learn what they're looking at. Astronomy is not like normal science. Normal science, you conduct an experiment. If you've ever done a science fair project, you know you start with a hypothesis. You develop an experiment that includes a control you have a variable, you take your data, you change your variable, you see the response, you interpret your data, and then that influences whether your hypothesis needs to be modified or if you understand what you're studying. In astronomy, we cannot alter any variables. We look through telescopes. We can't pick up a galaxy and look at it. We can't change anything. We can't say, what if we stirred that galaxy faster? What would happen? You just can't do that in astronomy. So what we do instead is we look at objects in the sky and classify them and try to find relationships between them. Now, in a normal experiment, you would make your changes and look over a time period for the change, how that change affects things. You might take a plant and subject it to green light and red light and to see what kind of light the plant responds to the quickest. You might do this experiment and a week later, took a couple weeks, maybe a month, I don't know. You have your data. Astronomy timescales are not like that. We see events happening that span millions or billions of years. So we can't just speed things up. We can't, I mean, our lifespan is too short to observe most of these changes. There are some events though, like supernovas and such, that happen very quickly. Problem is that we don't necessarily know where they're going to happen at. So it's not like you could just look and say, okay, that supernova is going to show up in a day. We don't know that yet. Someday maybe we'll be able to predict stuff like that. But we do catch supernovas in action. And so we do learn a lot about those short-term events in astronomy. Now, the other thing that astronomers have to deal with is we can only gather light from an object. We can't technically weigh something to see how much it weighs. We only have the light coming to us. But it's amazing how much we learn just from the light that enters our eyes, or more importantly, through telescopes and the instruments attached to them. So let's take a look now at what we see when we look at light coming from an object. And in this case, we're looking at the light from the sun. This is the sun spectrum, the visible portion of the sun spectrum. That means the light from, in wavelength terms, from red to violet. And this is actually a very long, stretched out spectrum, but it's been cut into segments and then stacked, okay? And what we see when we look at this high resolution image is all of these very little short width lines. Some of them are wider. And all of these lines are created by the elements in the sun's atmosphere. So we can learn something about the chemicals that are found on the sun. We can also from this learn something about the magnetic field. We can learn something about the temperature. We can also look at the sun visibly and see its shape. Similarly with lots of astronomical images, we can look at the shape and use this shape as a way of classifying the object. Now, this is only the visible spectrum. There is a whole lot more than the visible spectrum. This graph shows the visible spectrum here, but there is higher energy out to gamma rays and lower energy going through infrared, radio, and all the way out. So we need to, in astronomy, look at the entire spectrum. Now, telescopes work, and our eyes work in the visible range, radio telescopes for radio astronomy. And this graph is showing how much of the energy reaches the surface of the Earth. Some of it is blocked 100% by the Earth's atmosphere, which is good because it protects us. gamma rays are not friendly to us. So our Earth's atmosphere protects us from the gamma rays. And so to detect gamma rays, we need to have satellites in space. Another thing that we can learn from looking at the spectrum is how something is moving in relation to us. We can see that something is moving away from us or moving close towards us. We can also tell by looking closely at the position of a star, we can see it moving back and forth kind of as a large planet goes around it. So we can see some motion. Further away, it's harder to detect those motions, but closer to the Earth, to the sun, we can see that motion. So what we do when we look at an object or a group of objects is we can, I mean, this was done hundreds of years ago when they first started looking at objects with telescopes. They started classifying them, giving them names, looking for trends, like, you know, this kind of looks like this other object, so we're going to group them together and call them something. Over time, astronomers have developed models and simulations to try to explain the relationships between objects. We continue to observe, we continue to look for what's most important are the things that don't fit into our models, because that tells us where we need to modify our understanding. Going back to the hypothesis with the experiment, if your hypothesis isn't correct, you need to modify your hypothesis and then conduct more experiments. Same with astronomy. We model something, we say, oh, that doesn't quite fit with this observation that we've just received. We need to change the model. And then we continue observing and refining our models. So I want to so that you fully understand this, I want to talk about bugs, because we all kind of have a sense of what a bug is. You could, if you had the guts to pick up a spider, you could pick it up, look at it, count its legs, can do, interact with these objects. So it's not quite like astronomy, but it's something that you'll understand. So you're looking out in a garden and you see all these bugs, and you can classify spiders, bees, and beetles. And you're happy with this classification scheme. You think you understand the bugs that you're studying. And then along comes this guy. And you look at him and you say, well, he's not a bee. Could be a spider, but he doesn't look like a spider, but he's got legs sticking out. Certainly not a beetle. He doesn't spin a web, so that kind of says he's not a spider. When you first look at him, you say, he looks like a plant. He must be part of a plant. But he's not a plant because he moves around. What you've discovered is an object that no longer fits into your classification scheme. And so you have to change your classification scheme. And so you create a new class of a bug. So let's now move on to astronomy. So in astronomy, we see lots of stars, tons of stars. But we also see other objects through our telescopes that clearly are not stars. And in fact, there's tons of things that don't look like stars. And sometimes the technology allows us to look at something that we've never seen before. This last image here is the shadow of a black hole imaged for the first time, just recently in the last year. So let's start with the stars, because that's kind of one of the basic building blocks. A star, no matter the size of your telescope, always looks like a pinpoint of light. Now there's tricks that astronomers can do to kind of image the surface of a star, but for all general purposes, a star only looks like a pinpoint of light. Stars do come in different colors. They have different brightnesses. Sometimes the brightness is actually a function of their distance, so that a bright star may be actually a faint star, but it's very close to us. And so it appears bright to us. And a very bright star at a very far distance will appear very faint. So one of the things astronomers need to do is convert the brightness into something they call luminosity. That is like the true brightness of an object, removing the distance, the factor of the distance. So let's see how astronomers classify stars.
This is a Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort these stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness, the brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When the fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot, but even that runs out. They end up burning out as white dwarfs. Based on images for the Hubble Space Telescope, we've assembled a true plot that is a snapshot of the life history of stars in this ancient cluster.
Okay, so what they showed in that video is actually something called the HR diagram, Hertzsprung-Russell diagram. This is a very important diagram in the field of astronomy. What it is a plot of a star's color, which correlates to its temperature, and its brightness. And I'm meaning its true brightness, the luminosity. What we find is a lot of stars are plotted, when you plot the color and the brightness, a lot of stars land on this diagonal line. And we've named that line the main sequence. A star that is on the main sequence, that plots onto the main sequence, is very stable. It's producing energy at a stable rate. This is where the sun is located. The sun is located right about middle right there. And it will remain on the HR diagram for another 5 billion years. As it runs out of fuel, though, its temperature and its luminosity is going to change. And it is going to actually be found up in this area. Okay, so they would use the term, astronomers would use the term that the star has left the main sequence and has moved into the red giant area. It continues to burn, to work with the energy levels, the energy sources that it has, but eventually those will run out. The sun is currently using hydrogen, helium as a source of energy, but eventually that runs out and it will end up down here in the white dwarf area. Okay. One of the things that we can do with this graph, though, is tell relative ages of stars. So we can say that these stars up here, for example, Aldebaran is older than the sun because we know it's no longer using its initial source of fuel. All of this information comes just from the light that comes to us through our telescopes. We look at the spectrum, we learn the color, we can figure out the luminosity, and we plot it on the chart. So let's talk a little bit about the evolution of a star. But I'm going to go back to the bugs. butterflies in particular. A butterfly starts as an egg that hatches into a caterpillar, becomes a pupa, I call them a cocoon, eventually creating a butterfly. What's important is that the butterfly looks totally different at each stage of its life. This is an important lesson to learn when you're talking about stars. So let's look at stars. There are two loops that we believe that stars follow through a lifetime. Any particular star only follows one loop. One loop is measured in billions of light years, billions of years, billion with a B. The smaller loop is measured in millions of years, million with an M. So stars on this loop last much longer than stars on that loop. So let's first start talking about a sun-like star. So this is representing the sun. We believe all stars start out in a nebula. And in fact, the sun probably started out in a nebula, and several stars probably formed out of the original nebula. Over time, it becomes an actual star. And this arc of the loop represents that time that it's on that main sequence part of the diagonal line on the HR diagram, okay? Eventually it runs out of its primary fuel sources, becomes a red giant, and even further, it runs out of all fuel. It creates a planetary nebula. Now remember that name, planetary nebula, because I'm going to come back to that. The star itself is the little dot in the center here, but its atmosphere kind of sloughs off. And that atmosphere gets recycled into a new nebula and new stars. So it's the great recycle loop in the night sky. What remains eventually is just a white dwarf. Okay. Let's look at this other loop. This is the loop a massive star follows. Massive stars are energy guzzlers. They're burning they're converting their fuel so quickly into energy that they just don't last very long. They very quickly, over millions of years, quickly, astronomically speaking, become a red supergiant. That, once it runs out of all its fuel, becomes a supernova. Supernovas take place over very short time periods. The brightness jumps up very quickly over a few hours, and then it tails off over a few weeks time period. Now, what's important about supernovas is we believe that on the periodic table, if you've studied the periodic table yet, iron is located right here. It's believed that all the elements beyond iron, all the way through here, are all produced in a supernova. So if you're wearing any jewelry, the metal in the gold or silver in your jewelry was produced in a supernova. It's not part of the original Big Bang. What eventually ends up being left over after the supernova is a neutron star or a black hole. The difference being how large this massive star started out as. Okay, so we've seen this life cycle of sun-like stars and massive stars. And note that the objects all look different, just like the butterfly looks different. So let's go back to the graph or the photos of all the things that we see through telescopes. So we understand stars, we think, and how they're formed. And we also understand these are the planetary nebulas, the black hole, supernova remnant. We understand them. I wanted to mention planetary nebulas because we use the term planetary nebula has absolutely nothing to do with the planets. Way back when they were classifying objects, when they first turned telescopes towards the night sky and they could actually see these objects, they thought they were planets in the process of being formed. So they were called planetary nebula. We've kept the name, even though technically they have nothing to do with planets. They're actually the end life of a star. So we understand the end lives of stars. What's left are these guys. These used to be called spiral nebula. They thought these were possibly stars being formed. Well, you know what? That is wrong too. So let's learn a little bit about galaxies. Okay, so we now know that galaxies are well beyond our Milky Way galaxy. Used to be believed that, you know, they were stars forming within our own galaxy. And in fact, they thought the Milky Way galaxy was everything. Studying the spectrum of galaxies, they were able to detect that these objects are well outside of our Milky Way. And in fact, they're shaped similar to a CD in the sense that it's basically a round object. And I'm talking spiral galaxies, okay? It's basically a round object, but if you looked at it from the side, it's just a straight line. Okay, so its appearance to us changes depending on what angle we look at it from. Okay, all of the stars that you see in the night sky are within our galaxy. We cannot detect with our own eyes stars outside of our galaxy. Now at night, if you're in a dark site, you can see the Milky Way stretching overhead. That is part of the galaxy, our galaxy, that's so far away that we just cannot with our eyes resolve individual stars. So I have a video to show you that explains the classification of stars. So let's watch this.
Are all galaxies the same? We live on a planet in a single solar system inside a large galaxy made up of 100 billion stars. A supermassive black hole equal to the weight of a few million suns anchors the center of our galaxy. Our universe has hundreds of billions of galaxies, each containing stars like our sun. Galaxies range in size from ones with 1,000 stars to ones with 1 trillion or more stars. That means we have a lot of places to explore. Edwin Hubble was one of the first astronomers to discover that our universe isn't just sitting still, but it's expanding. Hubble also grouped galaxies by how they looked, because not all galaxies are the same. He described a few distinct types. Elliptical galaxies, which have no easily defined shape, with stars that move chaotically, and spirals or disk galaxies, which are flat, with pinwheel spiral arms that spread out from the center. As Hubble began to classify galaxies, he quickly discovered many galaxies didn't fit neatly into his categories. Was it possible that galaxies change from one type to another over eons? Even our own Milky Way galaxy has been changing. There are a handful of smaller galaxies, such as the Magellanic Clouds, Fornax, Sculptor, Leo, and others that orbit around us. The powerful gravity of the Milky Way affects these nearby galaxies, either causing them to be ripped apart or pulling them in to merge with ours.
Okay, so we watched how Hubble classified the galaxies, and he came up, like we saw in the bug example, something that doesn't fit the classification. And we will get back to those strange galaxies in a little bit. But right now I want to spend a few slides here to build a universe. We're going to use a CD. And this is a mental thing. I'm not actually going to do this, but mentally, we're going to place this CD with a photo representing the Milky Way galaxy on a football field at one of the goalposts. Okay. Note that this is not a photo of the Milky Way galaxy because we cannot take a photo of the Milky Way galaxy. We are in the Milky Ways. We can't take a picture of the Milky Way. But we believe it looks something like this. Okay. And we will place other galaxies at different distance away on our football field. Some of them will be this size, some of them will be bigger, some of them will be smaller. Now, on this model, I don't know if you can see it, but the center of a galaxy of the Milky Way would be here, and we are located out here. So we are located about an inch away from the center of the CD Milky Way model, okay? And it's at one of the end of a football field, okay? So let's proceed through building a universe. Okay, we're going to start with the Milky Way. The photo in this slide is one that I actually took of the summer Milky Way. This is looking towards the center of our galaxy. And this is the band that we cannot resolve as individual stars with our eyes. We can't even see that this well. This is a photograph where we can actually start to see some of the structure. What we see in the night sky with our eyes is just kind of like a cloudy structure. But in the summer, when we're looking this way, this dot represents the sun's position, and this represents what we believe the Milky Way galaxy looks like. And we would be looking back towards the center. In the winter time, we're looking out this direction. So the Milky Way is just not as intense when we're looking away from the center. So the summer Milky Way is an amazing thing to see. If you've not been in a dark site in the summer to see the Milky Way, you've got to do that. And like I said, this is at one end of a football field. The next closest large galaxy to ours is the Andromeda Galaxy. It's bigger than the Milky Way. We need a salad plate, something about 7 inches across. It's really pretty close to the Milky Way, though. It's about 8 feet away on our football field. Now, not too far away is the Triangulum Galaxy. In the night sky, if you were to hold up your hand, and let me stop share for a second. You hold up your hand and spread your fingers apart, those fingers apart. You spread those 2 fingers apart and hold it out. That's about how far apart in the night sky Andromeda and the Triangulum are located with, to each other. So they're relatively close together in the night sky. And they're also about the same distance away, 8 feet. But the Triangulum Galaxy is considerably smaller, about the size of a hockey puck. Now, okay, we're in Tucson. We don't play hockey too often, though we do have a hockey team. But a hockey puck is about 3 inches in diameter. Remember M33, the Triangulum Galaxy. That will come up later in the talk. Another galaxy is the Needle Galaxy. Now, this one is very similar to the Andromeda Galaxy, but it's looking sideways. So we see just the dust lane going across the center disk. It's about the same size as a salad plate, but it's 40 yards away. Now, because it's farther away, it's going to appear smaller in the night sky. Almost halfway down the football field here. This is the Whirlpool Galaxy. We may see this one tonight at the Star Party. It's 50 yards away. It's very similar in size to the Milky Way. It's a compact disk size, 5 inches across. But note this thing up here. That is another galaxy that it's interacting with. That's a little hint. Remember the galaxies that Hubble could not classify? Well, that'll come up in a little bit. Okay. This is another galaxy. This one is not spiral. This one is elliptical. Elliptical galaxies are like balls of stars. So this, instead of being a flat disk like a pancake or a CD, this is more like a softball. And it's almost at the other end of the football field. It's 80 yards away. And this was made famous not too long ago with the first image of the black hole that's at the center of that galaxy. That black hole is super huge, making it easier for us to detect it. You would think that this black hole at the center of the Milky Way would be easier to detect than something that's, quite a distance away from us. Remember, on our model, the center of our Milky Way, where the black hole is only an inch away. And now this one's 80 yards away. It's so much bigger than ours, it's easier to see. Plus, there's a fact that within our own galaxy, we have to look through an awful lot of dust before we can see the center of our Milky Way galaxy, where the black hole is located. So technically, it was easier to image this black hole than our own black hole. And we got one more slide here in our model. This is the Hubble Deep Field. The Hubble telescope stared at a patch of empty sky for something like a week. I can't remember for sure. Google Hubble Deep Field and you will learn all about this. But staring at a supposedly empty part of the sky, they were able to detect about 3,000 galaxies just in this tiny little patch. This represents the edge of the visible universe, the part of the universe that we can see. In our model, it is 10 miles away. There are trillions of galaxies between our goalpost mounted CD and that 10-mile distance. And we can see most of them, especially now with the James Webb Telescope coming online, hopefully very soon. Okay, let's move on to those peculiar galaxies that Hubble could not understand. They didn't fit into his scheme. Now, this video does not have any sound, so I want to introduce it a little bit initially. What they've done is modeled galaxies colliding, two galaxies similar in size colliding. And then this video will kind of freeze frame, rotate the model, and then we're going to see an image of a galaxy or a pair of galaxies that we see in the night sky through our telescopes. So this is the two galaxies coming just about in contact. And this is what we can see through our telescopes. So now the simulation is progressing. Now we rotate it because now we've seen something that looks like that. We couldn't understand that until we understood the simulations. And here's another pair. I'm always amazed at how much the view changes when you rotate an object. That looks like an S there. And now it's a figure 8. So this video, the way it's laid out, gives us some confidence in understanding the collision of two galaxies. Now, those are galaxies that are similar in size. And of course, you'd have to run different model simulations on different size galaxies colliding and such. But we have a fairly good understanding of galaxy collisions. So let's now look at the Milky Way galaxy and the Andromeda galaxy. The Andromeda galaxy is a galaxy that appears to be approaching us. Most galaxies are going away from us because the universe is expanding, but the Milky Way is approaching us.
Andromeda versus the Milky Way. Astronomers predict a titanic collision. Presented by Science at NASA. Imagine having a galaxy fall on your head and you survive the experience. NASA astronomers say that's exactly what's going to happen to our Milky Way galaxy approximately 4 billion years from now. New data from the Hubble Space Telescope confirm that the Milky Way is on a collision course with the great Andromeda galaxy. When the mashup occurs, say researchers, it's likely the sun will be flung into a new region of our galaxy. But Earth and the solar system are in no danger of being destroyed. After nearly a century of speculation about the future destiny of Andromeda and our Milky Way, we at last have a clear picture of how events will unfold over the coming billions of years, says Sangmo Tony Son of the Space Telescope Science Institute in Baltimore, Maryland. Astronomers have long known that Andromeda and the Milky Way were converging, drawn together by their mutual pull of gravity and an invisible dark matter halo that surrounds them both. But no one knew whether the far future encounter would be a near miss, a glancing blow, or a head-on smash-up. It all depends on the amount of Andromeda's sideways motion. A lot of sideways motion would allow Andromeda to sail wide of the Milky Way, missing our galaxy entirely. Less of it would bring the two galaxies directly together. The Hubble team, led by Roland van der Merel of the Space Telescope Science Institute, conducted extraordinarily precise observations of the sideways motion that removes any doubt. Andromeda is destined to collide directly and merge with the Milky Way. Although the two galaxies will plow into each other, stars inside each galaxy are so far apart that they will not collide individually. Instead, the stars will be thrown into different orbits around a new combined galactic center. Simulations show that our own sun will probably be tossed much farther from the galactic core than it is today. Team member Gertina Basla of Columbia University in New York describes what a head-on collision will be like. The stellar populations of both galaxies would be jostled, and the Milky Way will lose its flattened pancake shape. The two galaxies' cores will merge, and the stars will settle into randomized orbits to create a new, elliptical-shaped galaxy. To make matters more complicated, Andromeda has a companion, the Triangulum Galaxy, also known as M33. M33 is a relatively small galaxy, not nearly as large as Andromeda or the Milky Way. Nevertheless, it could play a big role. M33 will join in the collision and perhaps later merge with the Andromeda-Milky Way pair. There is even a small chance that M33 might hit the Milky Way first. Amazingly, Earth and the solar system should emerge from the melee unscathed. We'll just have a new galactic address, and perhaps a night sky with a double helping of stars. It turns out that a galaxy falling on your head isn't so bad after all. For more news about cosmic collisions and the future of the Milky Way, visit science.nasa.gov.
So that is going to happen in the distant future. It says 5 billion years. That's about the time that the sun will be moving off of the main sequence. So it'll be an interesting time. I hope you enjoyed today's presentation here. I'm going to put up a few links, and hopefully they'll appear in the chat. Go. A few other places you can find more information. NASA Space Place is a great place for kids to go to learn about astronomy. You can just Google NASA Space Place and it'll pop up. And also, if you want to learn more about the classification of stars, you can watch a Crash Course Astronomy, episode number 26. And that goes into a lot more detail than what I did today. So I hope you enjoy the rest of the evening. We will be looking at some of those galaxies and possibly some nebulas. I don't know what they're going to be looking at, but some of those objects. Now, I used Hubble images. We don't have a Hubble telescope at our disposal. The Hubble is well above the Earth's atmosphere and has very good resolution. Our telescopes are considerably smaller, so we don't have quite the amazing views, but it's still really cool to be able to locate those objects with our telescopes and see the light into our eyes or through the cameras in Zoom and such. Thanks for coming. Bye.
Hello, my name is Tom Sarko. I'm a member of the Tucson Amateur Astronomy Association. And for the next few minutes, I'd like to help you create a mental scale model of our place in our galaxy. And we may even go a little bit beyond that and talk about our galaxy's place in the rest of the universe. So let's get started. This is a picture of a typical spiral galaxy. Of course, it's not an actual picture of the Milky Way because we're inside of the Milky Way, so we don't have a photo of our Milky Way galaxy. But astronomers have figured out that this is a pretty typical looking spiral galaxy, and we'll use it to represent our Milky Way galaxy. So I think everyone knows the difference between our solar system, which then is a tiny, tiny, tiny member of our entire Milky Way galaxy, tiny by comparison anyway. And then our galaxy in turn is just one of many, many galaxies. We'll talk about how many a little bit later. So solar system, located in the Milky Way galaxy located among all kinds of other galaxies making up the universe. So if we're going to make a scale model, we have to first establish the scale. A map is a scale model, a globe is a scale model. But our challenge here is to make a scale model of our galaxy and our place within it. So our solar system is located about halfway out from the center of the galaxy, the nucleus or core of the galaxy. So this is actually a little bit too far. We'd be more right about there. And here's a representation of our solar system. This gives you a pretty good idea of the relative distances between the planets, but this does not even attempt to give you the relative sizes of the planets. You'd have to develop a different scale model for that. Pretty difficult to use the same scale for both those things, distance and size, in the same picture at least. All right, establishing our scale. For this scale model, this mental scale model that we're building together, we're going to let the distance from the sun to Pluto equal 1 inch, which is about the diameter of a quarter. Okay, so how big is the Milky Way galaxy? That's our goal using this scale. And the real distance across the Milky Way galaxy is about 100,000 light years. All right, well, remember what our scale is. The distance from the sun to Pluto will be 1 inch, roughly the diameter of a quarter. The real distance is 5.5 light hours. Now, remember, when we talk about light hours or light years, that's a unit of distance, not a unit of time. So a light hour is the distance that light can travel in 1 hour. And that actually equals about 670 million miles. So 5.5 light hours is actually equal to about 3.7 billion miles. So we're letting 3.7 billion miles equal 1 inch, which is about the diameter of a quarter. Okay, well, it turns out that on that scale, 1 light year would be about 133 feet, which means that 100,000 light years would equal, using our scale of 1 inch equals the distance from the sun to Pluto, 100,000 light years on that scale would equal about 2,500 miles. So that just happens to be about the distance across the North American continent. So our scale model would yield a Milky Way galaxy about the size of North America. And here's a picture reminding us of our scale. 1 inch equals the distance from the sun to Pluto. And on that scale, the Milky Way galaxy would be the size of North America. So there we are, superimposing that picture of a galaxy on North America. Now that's the distance across, but we should also consider the thickness so that we have a three-dimensional model. And where the solar system is located about halfway out from the center of the Milky Way galaxy, the thickness is about 1,000 light years. So how big would that be in our scale model? Get rid of this. Well, remembering that the distance of 100,000 light years in our scale model equals 2,500 miles, 1,000 light years is 1/100th of that. So if you divide 2,500 miles by 100, we get a scale distance of 25 miles. All right, so actually, let's go back for a second. So once again, just to remind you, if our scale is the distance from the sun to Pluto equals 1 inch, then the size of the Milky Way galaxy on that scale would be 2,500 miles across and about 25 miles thick. Now, this shows a picture of a commercial airline to try to give you some idea of what 25 miles is. Actually, an airliner would only fly about 7 miles high. 25 miles is about the distance from Tucson International Airport to the town of Vail or the town of Green Valley. So it's a distance that you could drive pretty easily within a half hour. To get to space is about twice that. An astronaut gets his astronaut wings if he flies to an altitude of 50 miles or higher. Okay. Now, we've got the size figured out in our scale model, but we need to populate it with stars. And astronomers estimate that the Milky Way galaxy has about 200 billion stars. Using the scale that we've created, each of those stars would be pretty small, only about the size of a bird seed that you would put in a bird feeder. And those are pretty tiny. They're bigger than a grain of sand, but not by too much. Now, someone has figured out, and I think we'll take their word for it, that 200 billion of those bird seeds would look something like the following. If you took a football field and built a 4-foot-high fence all the way around the boundary lines, sidelines, the end zones, and then filled that space, the entire field up to 4 feet high with bird seed, you would have about 200 billion bird seeds representing 200 billion stars. And it would look something like that. Okay, now we need to populate our scale model galaxy with all those stars. And we need to keep in mind that they actually are not spread out evenly. Okay, if we go back to our picture here, we see that about a third of those 200 billion stars actually are located in the core or the nucleus, and most of the other stars are in the spiral arms. We're located in one of the spiral arms, again, about halfway out from the center of the galaxy. And also stars are often grouped in clusters. And so far, our scale model has only considered stars. This picture is looking mostly at stars, but the galaxy also has things called nebulas, which are clouds of gas and dust. We have nebulas in which new stars are forming. We also have nebulas that are the leftovers of stars that have died. So just to kind of put those distances in perspective a little bit, the nearest star to us outside our solar system is Proxima Centauri. Its real distance is about 4.3 light years away. And in our scale model, that would be about 1/10 of a mile from our location. The nearest cluster of stars, this is a grouping of stars. The sun actually probably at one time was part of a multi-star system or a cluster. The closest star cluster to our to our solar system is 280 light years away. And in our scale model, that would be about 7 miles. The nearest nebula, the nearest cloud of gas and dust to our solar system, would be 410 light years away. And in our scale model, that would be about 10.25 miles. That's just the nearest nebula. And if we go outside our galaxy, the nearest large spiral galaxy similar to the Milky Way, but actually larger, is the Andromeda Galaxy. And using the scale that we've been using, its real distance is 2.5 million light years away. And in our scale model, it would be 62,500 miles away. That's roughly 1/4 the distance to the moon. The sizes of some of these things, that cluster would be 22 light years across, which would be about 1/2 a mile across. The nebula I mentioned, the nearest one is 4 light years across. That would be about 1/10 of a mile. And the Andromeda Galaxy is about twice as big as the Milky Way galaxy. It's about 220,000 light years across. So in our scale model, it would be 5,500 miles across compared to the Milky Way galaxy's 2,500 miles across. Now, this picture is what we'll sort of end our discussion with. This is just a tiny part of the sky. And it's an image taken by the Hubble Space Telescope of an area probably no bigger than the period at the end of a sentence. And yet it contains all these objects in that image. Now, the things that you see with these sort of spikes of light coming out, those are stars. And you see several of those in this picture. That's one, there's one, another one here, 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 here. But most of the objects don't have those spikes. And most of the objects in this picture, even the tiny ones, are actually other galaxies. Astronomers estimate that there might be something on the order of 100 billion galaxies in the observable universe. And each of those galaxies, on the average, would have about 100 billion stars on the average, typical size. So that would mean that all of the stars in the observable universe would the number of them would be about 1 followed by 22 zeros. So I don't know if that number has a name, but it certainly is a really, really big number. That number is roughly all the grains of sand on all the beaches on the Earth. So again, that would mean that an estimate of the number of stars in the observable universe, 100 billion galaxies with roughly 100 billion stars each, would equal all the grains of sand on all the beaches of the Earth. And remember that the sun is an average sized star, so it's probably a little smaller than one of those bird seeds. It's probably more like a grain of sand or maybe a tiny poppy seed. And by the way, on that scale, with the sun being the size of a bird seed or poppy seed, the Earth would be invisible. It would be microscopic on that scale. And it would actually be located about 3/100ths of an inch, tiny, tiny distance from that seed on that same scale. So I hope this has helped you sort of visualize the size and numbers that are often very hard to visualize in astronomy. And I hope it's given you a little better understanding of our place in our galaxy and even our place in the universe.
Okay, welcome back, everybody. We're still observing the sun. Again, I'm Jim Knoll with the Tucson Amateur Astronomy Association. And what we'll be doing now is, earlier in the program, we focused on sunspots and looking at the surface of the sun and talked a little bit about sunspots. And in between the two observing sessions, I did an activity called the magnetic sun. And that one went into more detail about what you will see and what's going on the surface of the sun and on the edge of the sun. And so now we'll be able to see what that looks like in real life and real practice by looking through Bernie's telescope. So with that in mind, let's go ahead and get started. And Bernie, if you want to take it over and show them a little bit about your equipment, and then let's take a look at the sun.
Thanks, Jim. And welcome back, everybody. And good afternoon, later afternoon now. We're going to start out quickly by showing you again what I have set up here. So here's an image of my telescopes as I have them set up in front of my home. There's two of them. The one on the left is will be displaying what's called a white light image. And the one on the right is a hydrogen alpha telescope to display a hydrogen alpha image. And you'll see the difference between the two of them. So let's start out with the white light image again. And here's our white light image of the sun. This is from the telescope I showed you on the left. The white light image is what most people have with their home telescopes. And white light image is called a broadband image. It gives you all the light, all the different wavelengths of light in the spectrum. And that's why you have a white image. Now, today, there's only one sunspot that's visible, and it's right there. And just make it out. I'm going to center it on the screen. It's that kind of dark flat patch there that is kind of dancing around in your image. It's a very small one, but I would estimate it at somewhere around the size of the Earth, or maybe just a hair smaller. And that's the only sunspot that's on the sun today. So that's what a white light image will give you. Now, let's take a look at the difference between a white light image and a hydrogen alpha telescope image. So I'm going to shift over to the telescope that you saw earlier on the right, which is a hydrogen alpha telescope. And as I mentioned earlier, The hydrogen alpha telescope looks at hot hydrogen at the alpha, what's called the alpha line of hydrogen. And that allows us to see things that white light telescopes or imaging can't. To begin with, again, these white patches are actually sunspots. And the white patchy area on the left is the one that you just saw in my white light image telescope. The one to the right is also a sunspot, but it's too faint to see in white light. It's just not there. Now, additionally, there are other surface features that you can see on the surface of the sun. And here's an example of one. This is called a filament. This kind of dark patch here is called a filament. And what that actually is, as Jim described to you earlier, is a flare or what's called a prominence that's jumping off the surface of the sun. But because it's coming towards us, it looks darker than the surface itself. So that's a relative thing. It's actually quite bright, but it's not as bright as the surrounding area. So relatively, it looks darker. And there's quite a few of them actually on the surface today. There's another set right up here. There was some more towards the top. I think we saw another patch up towards the top. We bring that up into view. There's another patch up at the top. So there's several patches of flares or prominences on the surface of the sun today of various size. Now, one of the other fascinating things that you can do with the hydrogen alpha telescope is look at prominences along the edge of the sun. When they are just coming around the edge or just receding on the far edge of the sun, they stand out against the black background of space. So we can actually see them more clearly. So by bringing up the contrast, I'm going to bring up the exposure level. So the surface is going to disappear. But as I bring the exposure level higher and higher, we'll actually start to see the prominences that are along the edge of the sun. Now, there aren't a whole lot of them today, but there are a couple. And let's see if we can zoom in on a couple of them. Here's probably the most obvious one towards the bottom. This is called a solar prominence. This is a hydrogen gas that's leaping off the surface of the sun. And typically that gas is following magnetic field lines. There's probably a big sunspot back around that edge that we can't see, obviously, but that sunspot has huge magnetic field lines. And those field lines allow for the gas to flow up along the field line. Now, these are fairly small ones. This one is probably no bigger than the Earth, maybe at most a couple Earths. But during the active period of sunspot activity, which right now will happen, or not currently, we're actually just past the minimum, coming back up on the other side of what's called the 11-year sunspot cycle. So we bottomed out about 2 years ago, and it's coming back up again to the peak, which will be another 8 or 9 years. At that time, there'll be many, many, many of these flares and prominences, and they'll be much larger. They can easily be 10 times the size of this little thing. But that's what's happening right now. Now, earlier, I was able to actually see the rest of the magnetic field line. I'm going to bring up a little bit higher and see if we can resolve it. It was there earlier. I don't see it now. No, it's not showing up like it was earlier. But earlier you could actually follow this curvature of gas as it looped around the line and came back down again. But I don't see it any longer. And it could be that that particular one is starting to fall back down to the surface. There's another smaller one right up here. There's an even smaller one right up here. I don't know if you can see those. I can see them here from my vantage point. And let's see, what else do we have? It's always fun to rotate around and see what we can find on the surface. Oh, here's another one. I have a bump. But here's another flare or prominence. Looks like a smaller one up here. It might be all the activity that we have today. Yeah, and we're back around to the one I looked at earlier. So those are called prominences. Now, most prominences will develop like the one you're seeing here, and it may hang around for a day or two and then fall back down to the surface as the magnetic field line pulls back to the surface of the sun. So the prominence just is a leap of gas that might go higher, might not, and then fall back down to the surface again. And I've actually seen some of these come up and fall back down again in a matter of half an hour or less. Most of them last for much longer than that. Now, occasionally, these magnetic field lines will disconnect. They'll actually leap off the surface so high that they disconnect from the sun. And the gas that's trapped into that field line keeps right on going out into space. When that happens, we call it a flare. And those flares, when they happen, go off into space in specific directions. Sometimes they'll come towards the Earth. When they do, then we get all kinds of effects into our ionosphere that affect the upper, what's called the upper atmosphere or the ionosphere of the Earth, and you'll get huge aurora. So we get aurora borealis in the northern hemisphere and what's called aurora australis in the southern hemisphere. And I don't know if you've ever seen aurora. Again, they tend to happen at the peak of the sunspot cycle, but they're absolutely beautiful to watch. And if you ever get a chance to see one, definitely take advantage of it. It also affects other things like communication satellites, and they can disrupt communications. It also affects high frequency communications. Ham radio operators are affected greatly by it. In some cases, it can benefit them, or in other cases, it can really degrade their ability to talk to one another. Another effect of huge flares hitting the Earth is that it can affect our electrical power grid and cause all kinds of disruptions to electrical power. There's been instances many years in the past, but there were instances several times where power grids failed and blacked out major sections of the East Coast. And there was another major one that happened up in Canada a number of years ago that shut down their electrical power grid and caused them a lot of difficulty getting it back up again. So those are some of the things that can happen when these big flares leave the sun and hit the Earth.
All right. Thanks, Bernie. That was an excellent discussion. There's some of it is are things that if you watch the magnetic sun activity that I talked about earlier was mentioned as well, but it's good to talk about some of the activities from the sun and how they impact what's going on Earth. So like Bernie mentioned, and I mentioned earlier in the magnetic sun activity that we're in a just beginning in the 11-year cycle. We're about a year into the climb, so we're still down pretty close to the minimum. And unfortunately, that means for us and observing the sun that there's just not as much to be able to look at. And so, it's always better when we have more activity, but the additional activity can cause other problems associated here on Earth. So it's a balancing act. All right. Well, thanks, Bernie. That was some great views and great discussions on the sun. So as you guys can see, not everything we do in astronomy is nighttime oriented. Sometimes we do some daytime viewing. And it's actually very important for scientists and for astronomers, and NASA and actually ESA, the European Space Agency, has a lot of telescopes, primarily space-based telescopes, but there's some ground-based telescopes as well that are focused on the sun, because it's important for us to keep an eye on the solar weather and watch what's coming off the sun and coming towards the Earth. So that if we need to take actions here on Earth, we're able to do that in a timely manner as it does it. So there's a lot of great activity, usually to look at the sun, and it's kind of fun to do that during the day. From the Tucson Amateur Astronomy Association perspective, we do, and later on we're going to have a nighttime star party. So hang with us. We'll be looking at some objects in the nighttime sky. But from the club's perspective, we do daytime events as well. Sometimes we'll look at the sun and do solar events at schools. And if there's a special event going on, we'll set up and do that during the day as well for just public events. So you can always check our website. There's a calendar on the website at tucsonastronomy.org. And we'll have lots of links at the tail end of this program that will allow you to, that'll help you find different fun astronomy things to be able to do. So yeah, definitely, especially if you're in the Tucson area, join us in some of the in-person events. But if you're not, we're going to try to continue doing virtual nighttime and probably some daytime events if there's something going on. So with that in mind, we're going to close out the solar viewing. Appreciate you hanging with us and taking a look at the sun. We'll have some additional activities. We'll talk a little bit more about the club a little bit later on. And then, like I said, tonight we're going to do a nighttime star party that we'll spend about an hour and a half or so looking at some of the cool nighttime objects. So again, I'm Jim Knoll from the Tucson Amateur Astronomy Association, and thanks to Bernie Stinger and sharing his telescope views with all of us. And so with that in mind, we'll sign off and we'll see you probably a little bit later on tonight for the nighttime star party.
All right, Jim Knoll here again, and we're going to continue our discussion. Earlier we talked a little bit about the sun, and we learned about the solar system. Now we're going to take a look at what eclipses are and why we have them. So we actually live in a very special time in our solar system. All right, the Earth is just the right distance from the sun, and we have a moon that's just the right size and just the right distance from Earth to create eclipses. It's not always going to be the case, and we'll talk about that here in just a minute. So there's actually two kinds of eclipses that we're going to talk about. There's solar eclipses, and there's actually two kinds of solar eclipses. There's a total eclipse and what we call an annular eclipse. And then the other kind of eclipse are lunar eclipses. So let's talk about solar eclipses first. Now, just like when we were observing the sun earlier, you want to make sure that if you're going to look at the sun, if you're not looking through a telescope, make sure you're wearing good solar glasses, approved solar glasses that will allow you to look at the sun, or some sort of viewer so that it doesn't hurt your eyes. All right, so let's first talk a little bit about the moon, because none of this could happen without the moon. When Earth was very young, so the Earth is 4.5 billion years old, so we're about halfway through our life. When the Earth was young and only maybe about 100 million years old and was still molten, so there was no ground to walk on, everything was like lava, what we think happened is that, at that time there was a lot more planets out in the solar system, much more than we have today. And we call them planetismals because they're planet wannabes. They're all kinds of different sizes, and some will mature and some won't. Well, what we think happened is that this large planet about the size of Mars, we call it Theia, slammed into the molten Earth, and Theia was molten as well. And when they collided, they actually merged mostly into each other, and Theia became part of the Earth. But what also happened is it spewed a lot of material around the Earth, and we actually had a ring around the Earth for a little while. That ring slowly coalesced and came together and formed the moon. Now, when the moon was first formed, it was only about 15,000. What's 15,000 miles away from the Earth. So it was very close and huge. It would have caused significant waves in the ocean once the oceans formed. The moon slowly has been drifting away, and now it averages about 235,000 miles away. It has a sliding orbit, and we'll talk a little bit about that later. So it's much further away. And the moon is important to stabilize the Earth, but it's also important for us to have eclipses. All right, so let's first talk about the solar eclipse. So when we have a solar eclipse, you've got the sun over here and the Earth over here, and the moon actually comes in between the Earth and the sun. And we'll show that in a demonstration here in just a little bit. When that happens, it'll actually cause a shadow to go across the Earth, and that's where it's totality. So if the moon is in the closer part of its orbit, then it will completely cover up the sun. And so there'll be no sun showing around. All you'll see is the chromosphere. We talked about the chromosphere earlier when we were talking about the sun. That's that layer kind of above the surface of the sun that we see. That's all that'll be kind of shining around the moon. When the total solar eclipse is going on, you can actually look at the sun and the eclipse without any kind of solar glasses. But the minute it becomes partial again and that total is over, you've got to go back and put on the glasses. And all the way up to the partial, you put on the glasses as well. All right, so we've got a total solar eclipse. That's how that happens. And now if the moon was further out in the orbit, so the moon's orbit kind of goes between about 218,000 miles out to about 248,000. And it can vary how far away it is. If it's further out, then it's going to be a little bit smaller. And what will happen is it won't completely cover the sun. And we'll have a ring of the sun will be around the moon. And that's what we call an annular eclipse. Now, for an annular eclipse, you have to wear the solar glasses all the time because the sun is still peeking around the moon. So you want to make sure you do that. Now, a total eclipse happens about every 18 months someplace on Earth. But in any one year, we can have several eclipses. We could have a total and an annular and a lunar, or we could just have an annular and a lunar eclipse. So it just kind of depends on what's happening within that year. Now, I told you the moon started off about 15,000 miles away, and now it's out to about average of about 235,000. Well, are we always going to have an eclipse? I don't know. The moon is actually drifting away from the Earth at about 1.5 inches a year. Now, it doesn't sound like very much. And how do we know exactly how much it is drifting? Well, every one of the moon missions that flew back in the late 60s and 70s, when they left, before they left a laser mirror there. And so now they bounce laser beams off the moon and they can measure the distance exactly. So it's drifting out about 1.5 inches a year. And in about 600 million years, the moon will have drifted far enough away that it'll no longer, even in its closest part of the orbit, will no longer cover up the sun. We'll only be able to have annular eclipses. So that's still a long ways away, so I think we're okay. So now what we're going to do is we're going to take a look at a demonstration of how the eclipse happens as it goes through. All right, so now what we're going to do is we're going to take a look at what an eclipse looks like from a demonstration perspective. The Earth and the Moon are not to scale here. We made them slightly different so that we could show the eclipse a little bit better. So as you can see right now, if you look back here on this white paper, you can see that the Moon is actually above the plane of the Earth. And like I mentioned earlier, the Moon orbits anywhere from 5 degrees above to 5 degrees below the plane of the Earth. So that's why we do not have eclipses all the time. So when the moon is just right in the plane, then as you see here, if you look at the Earth, you can see the little shadow going across the Earth. And that's where totality is. So that's where you want to be if you're going to see a total eclipse. So that was what a total and annular solar eclipse look like. Now let's take a look at lunar eclipses. Now lunar eclipses happen more frequently and are visible to a lot more people. When a lunar eclipse happens, that's when the Earth goes in between the sun and the moon, and the Earth's shadow gets cast on the moon. The lunar eclipse is visible to everybody on the dark side of the Earth. So if it's nighttime and it's dark and an eclipse is happening, you can see it. And we'll talk a little bit later on about when some of the upcoming eclipses are. So those are really, really cool. Now, as the eclipse happens, it'll go through the shadow of the Earth, and when it gets into the deeper portion of the Earth's shadow, that's when we start seeing the moon look more and more red. And the depth of the redness will depend on how deep the moon gets into the Earth's shadow. So the deeper it goes, the redder it will be. And what you're actually seeing is you're seeing all the Earth's sunrises and sunsets across all the planet at one time. So what's happening is the sun's light is being refracted around the Earth, and it's going through the atmosphere of the Earth, and that's a fairly thin atmosphere we have, and it's being reflected back on the moon, and that's the redness that we're seeing when we get into a total eclipse. So lunar eclipses happen over a long period of time. When we're talking a solar eclipse, totality may only be a couple of minutes long, maybe up to 6 minutes if you're really in a good total eclipse. And the people that are able to see the total eclipse are only about 50 miles wide, the shadow that passes. So you have to travel to where the total eclipse is. But with the lunar eclipse, it's visible to everybody on the dark side, and it's going to last for 4 or 5 hours. So what we'll do now is we'll show you what happens visually when the Earth passes in between the moon and we have a lunar eclipse. Okay, so during a lunar eclipse with the Earth in between the moon and the sun, what happens, if you look back here, it's probably easiest to see initially. If you look on the white paper, you can see as the moon drifts into the Earth, you can see that now if you look at the moon, you can see it's starting to take a bite out of the moon. And as it goes further and further, there's a partial eclipse. It's getting more and more until you get into totality, where the moon's or the Earth's shadow covers the moon. And that's a total lunar eclipse. And that's where it'll get into the deep red hues. So that gives you an idea of what happens during a lunar or solar eclipse and what happens during a lunar eclipse. So when we're going to have an opportunity to see some of these things? Well, we have a couple of solar eclipses coming up. The first one is going to be October 14th, 2023. So that's in 2.5 years. And that's going to be an annular eclipse. So that's, again, when the moon doesn't quite cover the entire sun. There's a little ring around it. And that one's going to come in the northwest and go through the Midwestern states and exit out through Texas. So it's going to kind of cut a swath through there. Again, you have to be underneath the 50-mile wide path of the moon's shadow to be able to see a true annular. And the closer you are to the center line, just like with a total eclipse, the longer the duration of the eclipse will be, and it'll be even and it'll be much more centered. If you're outside of that path, then you can still see the eclipse, but it's only a partial eclipse. So for a total and even for an annular, if you have the opportunity to go into the path of totality or into the path of the full shadow, you should really take advantage of it, because it is it should be on everybody's bucket list. And it really, the pictures don't do it justice. It's much better to be able to view it in person. So that's the next annual eclipse. That's October 14th, 2023. The next total eclipse in the United States is going to be April 8th, 2024. So about 3 years from now. And that one is going to come in from Texas, go across the eastern states, and exit out through Maine. So again, you're going to have to move east. If you're in the western part of the state, you're going to want to go over to where totality is. Totality will only last for a couple of minutes, but it'll be really, really cool to be able to see. So those are the next solar eclipses. We have four. I think we have four. Yeah, we have four or three. We have 3 lunar eclipses coming up. The next one is going to be May 26th this year, 2021. So just a little bit in a couple of months. And it's going to be in the wee hours of the morning. It goes from about 1:45 in the morning to about 5:30 in the morning. So maximum eclipse is about 4 o'clock in the morning. So in that one, if you want to see it, you can set your alarm, get up about 4 or so, and go out, and the moon will be in full eclipse. Those times are all for Tucson. So if you're not in Tucson or in Arizona, you'll need to adjust the timing for your time zone. All right, the next one after that is going to be May 15th, 2023. So a year, or 2022. So that'll be a year from now. And that's going to happen in prime time. It'll start with a partial eclipse about 7 p.m. and end about midnight, with the maximum eclipse where the moon is fully in the Earth's shadow at about 9 p.m. So for those of you in Tucson, we will most definitely, for TAAA, we'll be setting up an event someplace, I'm sure, to be able to look at the eclipse through some telescopes and be able to enjoy it as a group. So that's May 15th of next year. And then a little bit later in that year, November 8th of next year, there's going to be another one in the wee hours of the morning. So we actually have 2 next year. And that one will be about 1 in the morning till about 7 in the morning, with maximum about 4. So 2 opportunities to see solar eclipse in the next 3 years, and 3 opportunities to see lunar eclipse. So I hope you've kind of enjoyed our in-depth discussion on eclipses. There is, especially if you have kids, there's a really neat place to be able to go, and that's if you go to the NASA's website, nasa.gov, they have a web page called NASA's Space Place. And if you go there, you can see all kinds of space-related activities for kids and for adults. And with that in mind, we're actually going to play a video from NASA's Space Place that talks about eclipse. So stay tuned for that right now, and we'll see you during the next eclipse.
Space Place. In a snap. Whoa! It's the middle of the day. So why is the sky getting dark? It's a solar eclipse. A solar eclipse happens when, at just the right moment, the moon passes between the sun and Earth. Sometimes the moon only blocks part of the sun's light. This is called a partial solar eclipse. Other times, the moon blocks all of the sun's light. This is called a total solar eclipse. As the moon blocks the sun's light, it casts a shadow on part of the Earth. The moon's shadow creates a trail as the Earth rotates. This trail is called the path of totality. If you want to experience total darkness during an eclipse, you have to be in the path of totality. In that path, the moon completely blocks the sun's light for a few minutes. It gets so dark that it looks like nighttime during a full moon. If you don't know what's happening, it can be confusing. Animals can get confused too. But this total darkness can also be kind of cool for scientists who study the sun's atmosphere, called the corona. The corona is very dim. It's usually hard to see because the sun is so much brighter. But when the moon blocks the sun's light during an eclipse, all you can see is the light from the corona. Total solar eclipses over the land, where people can see them, don't happen very often. But when they do happen, the moon gives scientists, and the rest of us, a glimpse at the corona's beautiful streams and ribbons. Thanks, Moon! Find out more about the sun at NASA Space Place.
Hi, I'm Terry Lappin. We're going to do an activity called Pocket Solar System. At the end, you will have a model of the orbits of the planets that you can roll up and put in your pocket. So let's get started. The materials you'll need are 2 pieces of paper. Plain white paper is best. You can also use adding machine paper. In this activity, we're going to use the regular paper. If you're going to use the adding machine paper, you want about 4 feet worth. You also want tape if you're using the paper, a pen. I like to have a ruler handy, and scissors. You don't have to have scissors, you can tear things, but we can use the scissors too. An add-on activity, if you're using the paper, is illustrations of the planets that you can download from our website. Okay, let's get started. We're going to take 2 sheets of paper and fold them in half and crease them. You can use the ruler to get a nice sharp edge. And then you can use the scissors if you want to cut. I'm just going to tear it. And we're going to do that to both sheets of paper. Fold it lengthwise, crease it, and then we'll tear it. And now we want to make a long strip. So what we're going to do is lay these pieces together like this and tape them together. And I'm going to put tape on both sides of the paper. You want to overlap them just a tiny bit, maybe a ½ an inch. Putting tape on both sides holds it together a little bit better. So we're going to do that real quickly to make our strip. Try to line it up so that it stays relatively straight. One more. Now, as you probably noticed, I put too much tape on. And so I'm just going to use the scissors now. Just trim that extra tape off the edges so it doesn't catch on things. All right, that looks pretty good. All right, so we've got a long piece of paper. All right. Now let's talk about the planets real quickly. This is the order. They're all crunched up here, really close together. They're not really like that in real life. But we've got Mercury, Venus, Earth, and Mars. These are called the terrestrial planets. They're kind of like the Earth, solid surface that you can walk on. Maybe in a spacesuit, but you could walk on them. The outer planets, Jupiter, Saturn, Neptune, and Uranus, are gaseous planets. They don't have a hard surface that you can walk on. At least we don't know. All we can see is the clouds in the atmosphere. And then we've got some strange objects, asteroids, and Kuiper Belt objects. The largest asteroid is called Ceres, and one of the most famous Kuiper objects is Pluto. So this model is going to include all of these planets. So we're going to start this way. Take one end of the paper and with a pen, write sun. Write it kind of small, not too big. Okay? And you'll see why at the end. And at the other end, you can put Pluto or Kuiper objects. Okay, so I've got Pluto at one end, the sun at the other. Put them together, fold it in half, use your ruler to crease it, and then open it up. Now you've marked the center of the line. Let's put a line on that fold. Okay, there we go. That marks the center between the sun and Pluto. Now you might think that the center planet might be Jupiter. You'd be wrong, because at the center between the sun and Pluto is actually Uranus. So let's write Uranus on that line. That marks the orbit of Uranus. Okay? Now, take Pluto, or the Kuiper objects, and fold it to the line where Uranus is. Increase that. Open it back up and mark that line. Whoa. Next one out from Uranus is Neptune. Okay, we are done with the outer solar system. Now we have to fit all the other planets, Saturn to Mercury, into this amount of space. It's going to get crowded. We're going to fold the sun into Uranus. Okay. Open it back up. Mark that line, that fold with a line. And that one is going to be Saturn. So far, so good. Fold the sun to meet Saturn. Crease it. I think you've got the routine down here. Mark a line. That will be Jupiter. Again, fold Saturn to meet Jupiter. Mark the line. What planet do you think might be there? You might think Mars. Oh, you'd be wrong. Remember the asteroids. We have to include the asteroids. So just write asteroids here. And you could also mark Ceres. That's the largest asteroid. There's hundreds of thousands of asteroids. Okay, this is where it gets really crowded. Fold the sun to meet the asteroids. crease it. Mark that line. This is Mars. Oh boy, we have to fit Mercury, Venus, and Earth into a tiny little space. Fold the sun to meet Mars. Don't unfold it this time. Fold it again to meet Mars. So you've done a double fold. And then open it up, and now you have 3 lines. And we're going to mark all 3 lines, all 3 folds with a line. 1, 2, and 3. Okay. These we'll just mark in order. The top one nearest the sun is Mercury. And now you see why I said write the sun really small. The next one is Venus. And then one other planet. Which one have we not done? It's the Earth, of course. So let's put the Earth in here. Now let's look at the whole thing. The sun at one end, Pluto at the other. Look at all the open space in our solar system. Lots of open space. This marks just the orbits. Now, there's an additional activity using the illustrations of the planets that you can download from our website. And you can cut these out and you can attach them, glue them onto your strip. Now, if you use the adding machine paper, it's not going to work because it's going to be difficult, at least. Jupiter is wider than your piece of paper, so it might be a challenge. You can print this out at a smaller resolution, smaller size, like a half a sheet. That might fit better. When you attach all of the photos, you'll have to scrunch all of the small planets together. I did them kind of stacked like that because it's so crowded there. Notice that Jupiter is as wide as the paper. If you put it on the line, it's going to cover up Jupiter. I chose to put it below the line. You could put it on the line and then write the name Jupiter someplace nearby. And Saturn, because it has the rings, I had to twist it on its side. Okay? Now, the distance and the size of the planets are to 2 different scales. If we were to use the pictures and mark it on a piece of paper, that paper would have to be several miles long. Now, do you think you could roll that several mile paper up and fit it in your pocket? Just don't think so. So here we have the distances to the planets, the order of the planets, illustrations of the planets to 2 different scales. You need to remember that you can now roll up and put in your pocket. Keep it with you so you always know what the order of the planets are. So we're going to be looking at a video very soon that actually does the scale of the planets and their orbits to the same scale. And it's so big they have to drive a car. This is Terry Lappin with the Tucson Amateur Astronomy Association. Thanks for joining us.
What is a nebula? This is a nebula. It may look like a colorful work of art, but it's really a giant cloud of dust and gas in space. Nebulae are far away from Earth. We know what they look like because scientists use powerful telescopes to capture images of them. A nebula can take many different forms and shapes. But where did these stunning dust clouds come from? Some nebulae come from the gas and dust thrown out when a dying star explodes. When a massive star explodes, it's called a supernova. This is an example of what that looks like. Other nebulae are regions where new stars are beginning to form, called star nurseries. How does a nebula make stars? Well, nebulae are made of very spread out dust particles and gases, mostly hydrogen and helium. Gravity begins to pull clumps of dust and gas together inside the nebula. Then, as those clumps grow larger, their gravity gets stronger and stronger. Eventually, a clump of dust and gas gets so big that it collapses from its own gravity. This collapse causes the material at the center of the cloud to heat up, causing the beginning of a star. The closest known nebula to Earth is approximately 700 light-years away. It is called the Helix Nebula. The Helix Nebula is the remnant of a dying star, like what will happen to our own sun in a few billion years. Using powerful space telescopes like NASA's Spitzer Space Telescope and Hubble Space Telescope, we have captured images of the Helix Nebula and many others. Scientists will learn more about nebulae with NASA's James Webb Space Telescope. It will be able to look through the dust to see stars forming planetary systems. Learning more about these faraway nebulae help us better understand the life cycle of stars, including our sun, the most important star to our life here on Earth. Learn more about our universe at NASA Space Place.
We live on the surface of a planet, spinning on its axis once every 24 hours. Its rhythms of day and night are embedded in the biological makeup of all life. During the day, we bathe in the glow of the sun. As night approaches, darkness takes over. It's a time to rest, to rejuvenate, to marvel at the beauty of the night. Until just over a century ago, our night skies were very dark. Now, even the wilderness is invaded by light. Our cities glow at night. Buildings are lit up. Unshielded lights blind us as we travel along our streets and roads. All these artificial lights overpower the darkness. The waste of energy is obvious, even from space. Much of that yellow glare the astronauts see comes from streetlights. They produce most of the light pollution on the planet. The glare is scattered by the atmosphere, creating sky glows over the landscape. We are losing the dark of night at the speed of light. Light pollution threatens the health of every living thing on Earth. Lights at night disrupt plant growth. Unshielded lights contribute to the deaths of countless land and sea animals each year. Migrating birds crash into illuminated buildings. Newly hatched sea turtles mistake the glow of electric lights for the shimmer of the ocean's surface. Bright lights at night also directly affect humans. Drivers and pedestrians temporarily blinded by poorly designed lights have suffered tragic accidents. Light pollution poses a silent threat to our health. Exposure to light at night disrupts the circadian rhythms that regulate our sleep cycles. People working at night under bright lights or living in light-polluted cities face a higher risk of developing diseases such as breast and prostate cancer. Here is a night sky with typical light pollution. On a good night, only the brighter stars and planets pierce the glow. This is what the night sky might look like if we could remove the light pollution. That faint band of light stretching across the sky is the Milky Way, our home galaxy. Because of light pollution, many people have never seen it. Astronomers know all too well the problems caused by lighting up the night. They need clear, dark skies to study the many fascinating objects in the universe. Light pollution simply washes out their view of the cosmos. Lighting up the night sky wastes money and fossil fuels. To keep a 100-watt light bulb turned on every night for a year takes the equivalent energy output from burning half a ton of coal. Multiplied by the billions of lights blazing up from Earth, the cost of energy we use to light up the night is colossal. While lighting is needed, there are some simple things we can do to ensure that it's neighborhood-friendly, energy-efficient, and helps preserve dark skies. We can replace light fixtures that send light up to the sky with ones that direct light down, exactly where we want it. They're called fully shielded fixtures. We can also illuminate only the places that need it. And of course, we can just turn off unnecessary lights. These are smart ways to use lighting. They offer simple solutions to problems caused by light pollution. We have a choice between wasting resources by sending light to the sky or learning to use light more responsibly. Light pollution is a problem each of us can help solve. Together, we can bring back the dark of night to planet Earth.
Hi again. We're back and we're going to talk a little bit about the Tucson Amateur Astronomy Association. We call it TAAA. Once again, here's our president, Dr. May Smith.
The Tucson Amateur Astronomy Association, or TAAA, has provided service to members and the astronomy community and the public since 1954. That is 67 successful years. We have almost 500 members. We provide many different activities that are available for members to improve their observing skills or to just learn more about astronomy. TAAA hosts monthly meetings, which are currently virtual and open to the public. In the future, we plan to resume in-person meetings, but continue the virtual component. Each meeting provides both a public and an additional private component for members only. We access the resources of our very knowledgeable and renowned astronomy community to obtain guest speakers on latest developments in various astronomy topics. TAAA provides different special interest groups where our members can experience and share astronomy in smaller group settings. Terry and Jim will discuss some of these in greater detail later. TAAA has 2 dark sky observing sites that are available for member use. One is about 100 miles southeast of Tucson near the Chiricahua Mountains, which is an extremely dark site, and one on the west side of Tucson near the Saguaro National Park West. Jim will talk more about these later. We also have a lending library with books and other astronomy materials. And we have a telescope lending opportunity for members in which they may try out different scopes and borrow them on loan if they don't have a telescope or if they want to experiment about what kind of telescope they may wish to purchase. We have a website with a lot of information about the club and astronomy in general at the TucsonAstronomy.org site. Dues are very modest at only $25 for an individual member and $30 for a family per year with discounts as well.
Thank you, May. As she mentioned, we have special interest groups. Currently, we have 3 special interest groups. One is for outreach, one is for astroimaging, and the other one is for beginners. The Starry Messengers group is our outreach group. We've got several programs that we run through the outreach program. One is the library telescopes. Now these are telescopes that you check out from the public library. They're 6-inch telescopes, and they're at different locations. There's one at the downtown main library, the Oro Valley branch, the Miller Golf Links branch, Valencia branch, Sam Lena South Tucson, and also the Kirk Bear Canyon branches. So you check these telescopes out. We do have a video that you can watch online that tells you how to use the telescope. And then you return it back to the library, and somebody else can check it out. Now, these are 6-inch telescopes. May mentioned a lending telescope program that the club also has. Those are for members, and they are much bigger telescopes, require a bit of training to use. But the library telescopes are more user-friendly. Kids can operate them with adult supervision, and you can watch the video and see how it works. That video is on our website. The beginners group we call Astronomy Fundamentals. They take people from, I have a very enthusiastic interest in astronomy, but I don't know how to use a telescope. Or somebody may say, somebody bought me a telescope and I don't know how to use it. Our beginners group takes beginners and helps them use their telescope. Or we also have a class, usually it's 3 Saturdays in a row, class to learn general astronomy. It tends to be more observational because we are more observing type astronomy club rather than a professional doing research. But you will learn a lot of astronomy. Now, unfortunately, with COVID, we were not able to run our classroom program, but hopefully next year we'll have that. That's through the Astronomy Fundamentals, and it is only for members. It's free for members, but you do have to join to be a member and to take that class. Our other third special interest group is the astro imaging people. They take some fantastic photos. And I am not going to lie, it takes a little bit of skill and patience to take some really nice photos. Now, it's a way better than it used to be 20, 30 years ago, because you can do that. You can take fairly decent photos with your cell phone. The photo that's in our background here was taken with one of the library telescopes through my cell phone. So you can take decent photographs of astronomy objects with minimal equipment. But our astronomy imagers, they go all out and take some really fantastic photos. And what they're able to do through a special interest group is, because it's a smaller group, you maybe have 20, 30 people, they share their experiences, they learn from each other and improve their own skills. That's one of the biggest reasons for joining an astronomy club, is to learn from other amateur astronomers. I studied astronomy in college. It's way more fun hearing it from your friends and learning from each other. The Astronomy Club also is associated with several other organizations. We are members of the Astronomical League. We're also part of the Night Sky Network, which is through NASA. And we also work with Kit Peak occasionally, and the International Dark Sky Association. Now, the IDA, International Dark Sky Association, was co-founded by one of our members. And they are headquartered here in Tucson, and they do some fantastic work trying to reduce light pollution, which is it's a waste of energy, and we lose this night sky. All of those organizations are described on our website. I really encourage you to look at our website. We've got lots of information there. Information about our special interest groups, information about these other organizations. You can also join through the website. And of course, you can make a donation to our wonderful organization. And you won't even be a member, but you can make a donation. Some people just want to help us out. I think we're now going to go to Jim Knoll. He's going to talk a little bit about our outreach program through the school programs.
All right, thanks, Terry. So as Terry was mentioning a little bit under the Starry Messenger SIG, one of our primary missions at the TAAA is outreach. And before the pandemic hit back in 2019, we actually did over 225 outreach events in 1 year. Now, a lot of them are open to the public. We do a lot of them for schools. We'll support nonprofit organizations. We also will do some of the parks and recreation and things like that. And then we also offer the paid events that we can do. And some of those would be like private star parties or supporting some of the resorts in Southern Arizona and their guests. Most of these are done in person, but like most other organizations, last year we kind of had to pivot to doing more and more virtual. Some of our early virtual events, if you check them out on Facebook or YouTube, are a little rough around the edges. But we did get better as we went along. Hopefully we got better. And I think everything, we're now getting pretty good about it. They are, like I mentioned, all of our virtual events are on our Facebook page and on our YouTube channel. We've done 10 so far since March of last year. Even when we get back into doing in-person events for schools and the public and things like that, we plan to keep doing virtual events, probably once a quarter, because we have the ability to reach many more people than just the, those in Southern Arizona. We can reach out to some people that are maybe in light polluted areas, or have excessive clouds or something like that, and be able to share our astronomy outreach with them. If to kind of keep up with everything we're doing, there is a calendar on our webpage. So if you go to the website, there'll be an events calendar. We also post events on our Facebook page that lists upcoming events. They're not quite as far out as the calendar are. Those are the two sources. The nice thing with the Facebook events is if you follow one of those because you're interested in it, if we decide to cancel it because of weather or some other issues, then you'll get notified about it as well. They are all streamed to our Facebook page and YouTube channel. So just to kind of give you an example of why, I have over 60 volunteers that help support the outreach mission. And to give you an idea of why we do that, we've got a little video for you to watch that just kind of shares the joy of being able to share astronomy with the general public. And it's called A New View of the Moon. So here it is.
One night I was bored in my apartment and decided to take my telescope out to the sidewalk. The moon was out and I thought, why not? Within a few minutes, people started walking over and asking what this thing was.
Hey, what is that, bro?
It's a telescope.
Oh.
Do you want to check out the moon? Do you want to take a look at the moon?
What is it?
It's the moon.
Where am I supposed to look?
You're supposed to look right here.
Oh, in there.
Yeah. That's where it all started, and it just sort of went from there.
I'm looking at the moon. Hold on real quick. Hold on. Oh my God.
Oh my God.
Oh my God.
Oh my God. I can't believe it.
Oh my God. Oh my God. No way.
No way. No way. That's the moon?
No way.
Yeah, way.
No.
Well, you can see the craters. Yeah. That is so cool.
Oh, not that.
Get closer. Get wider.
Whoa. What? Look at the edge. I want to see more of it. I know.
Holy.
I've never seen this before.
I've never seen this before like this, man.
Wow, that is intense right there, boy.
Woo! Bro, that look like that's right down the street, man. Man, what you got here, man? That look like that's right down the street.
Yeah, isn't that amazing? It's right.
Is that an actual image of the moon? Is that like a live image?
It's that right there. To be able to see it up close and feel like you could almost reach out and touch it, and that's what makes it real to us.
That is incredible.
I kind of felt like I just landed on the moon.
it makes you realize that we are all on a small little planet and we all have the same reaction to the universe we live in.
Wow.
Whoa.
Wow.
Oh, wow.
Wow.
Yeah, wow.
I think there's something special about that, something unifying. It's a great reminder that we should look up more often.
All right, hopefully you enjoyed the video on the moon and the outreach activities we do. Kind of gives you an idea of why a lot of our members really enjoy doing astronomy outreach. As May mentioned earlier, we also have a couple of observing sites for the club. We have one that we own in the Chiricahua Mountains called the Chiricahua Astronomy Complex, or what, as we call it, CAC. It's 16 acres with several observatories. There's space for personal telescopes. We have pads with electricity. There's RV and tent camping. Soon we're gonna have some sleeping rooms. And one of the things I'm really excited about for outreach is we're gonna have a learning center with classroom. So we're gonna be able to bring youth groups and schools and other organizations out to CAC and talk astronomy in the comfort of a nice classroom, and then go outside and observe under some incredibly dark skies. We also have access to a dark site on the west side of Tucson, near the Saguaro National Monument West, and it has a telescope as well as some pads to observe. We don't own this site. We have a lease arrangement. It's with the Model Airplane Park. But it works really great because they usually do stuff during the day and we can use it at night. So it gives our members a chance to use either one of the sites to be able to observe from. And we will normally hold monthly events at both of these sites so that you have the opportunity to come out and you know, if it's the first time out to one of the sites, you can just come and observe, or you can bring your scope out and there'll be other members around that can help you learn how to use it. We also open CAC twice a year to our neighbors and the general public around Tucson or around Southern Arizona. And we call this Evening Under the Stars. We usually do it twice a year. Hopefully we can get back to it in the fall, we'll see. But we're really excited about being able to open up the site. And it gives our neighbors a chance to see what we are getting excited about and what we're doing, and just makes it a little more harmonious. So that's kind of some of the benefits of belonging to the club. And we have areas that appeal to just about everybody. So no matter what you want to do, I think you can enjoy being a member of TAAA. Terry, back to you.
Thank you, Jim. I want to mention a few items before we get on with our observing. And that is, Jim mentioned our observing locations. Now, CAC is open a couple times a year to the public, but otherwise our observing sites are for members only. So that's another member benefit. We also have a monthly bulletin that goes out to our members that describes all of our events and our meetings. We've got 3 upcoming meetings scheduled at this point in time. We believe they will all be virtual at this time, but we'll see how it goes towards the summer. And I just want to mention the ones that are coming up. May 7th will be a virtual event, so the public can attend this through Facebook. We will be listening to Christine O'Donnell. She's just received her PhD from the University of Arizona. So it's Dr. Christine O'Donnell. She's actually located up at ASU up in Phoenix now. She went from a Wildcat to a Sun Devil, so okay. She's going to talk about galaxy formation, and that is at 6:30 p.m. on May 7th. Our June 4th meeting will be given by Joe Wright. He is a TAAA member, but he is, I believe, going to be in Missouri at the time. And so that will be a virtual event simply because he will not be in Tucson. At least that my understanding is he won't be. He's going to talk about observatory construction. Some of our members have some fantastic observatories in their backyards. Some of us have telescopes that we wheel out and observe. Others have permanent structures in their backyard. And Joe has some experience talking about or building an observatory. So he's going to talk about his observatory. And then July 2nd, we have another TAAA member, Rick Hill, who's going to talk about the solar activity on the sun. We are coming out of the low point in the sunspot cycle and starting to climb up towards solar max, which will be in about 6 years or so. And so Rick Hill is a member of the Association of Lunar and Planetary Observers involved with the solar section. And he'll bring us up to date on what the sun is doing as of July 2nd. Okay. And hope you join us through Facebook online if you remain in the public. And if you join us through the club and become a member, you can come join us through Zoom. And then you can participate in some breakout rooms that we have, discussions and such after the Facebook feed ends. Okay, thank you for coming tonight. Let's get on with some deep sky observing.
Hello, I'm Jim O'Connor from the Tucson Amateur Astronomy Association. Welcome to our 2021 Virtual Astronomy Festival. In this presentation, we'll take a journey across the night sky and explore some markers to guide us both from our Western point of view as well as from some other cultures. Since this presentation was recorded earlier, if you have questions or comments, please enter them in the chat window and we'll try to get you an answer during the presentation. Let's take a look at the night sky. Right now, you see how the sky would look in Tucson, Arizona on April 17th, looking north at about 7 p.m. or 7:45 p.m., with the sun having set a short time earlier below the landscape horizon. As we look to the north, the sky appears without guideposts to help us explore. We'll change that shortly when we will explore markers we can use to guide our way through the night sky. When the Cherokee would look up to the sky, they would see the stars as spirits of people who have left us and spirits that have yet to be born. So we only spend a short part of our existence here on Earth and should make the best of our stay. We've removed the artificial landscape and discover some of our culture's markers. The 20th century began in multicultural astronomical chaos, of many cultures' observations without references to common nomenclature. In 1929, the International Astronomical Union brought order from the chaos by decreeing the stars would have their original Arabic names, planets would have their Roman names, and constellations would have their Greek or Latin names. This is generally called the Western folklore, and these characteristics will help guide our tour of markers. First marker would be Polaris, located at the elevation above the horizon, equivalent to the observer's latitude. I'll point out Polaris here in the circle. It seems to stay fixed while the sky rotates around it. Polaris shares our northern view with the Great and Little Bears, Ursa Major and Ursa Minor, and other collections of stars. There's Ursa Major and Ursa Minor. You'll need to use your imagination on the little bear, Ursa Minor, as we see only the Little Dipper. Legend says that the bears were terrorizing villages and were thrown into the sky by their tails. In a dark location, prominent in Ursa Major are the nose, the front shoulders, and the feet. Which are also called deer tracks by some Native American cultures. Ursa Major also has a prominent asterism, or grouping of stars, we call the Big Dipper. While the Big Dipper appears as a ladle to us Westerners, to others it is called the plow or the ox cart, or even from Hindu lore, the elephant of creation. One prominent constellation in the air in that northern area is Cassiopeia. Opposite the bear, the big W or M representing the very vain queen of Ethiopia. Jealous of her daughter Andromeda's beauty, and because of her vanity and other evil acts, she's been chained to a chair by Zeus. So she has to look away from Olympus and spend half of each day upside down, as she is at this time. Next to Cassiopeia is her husband, Cepheus, who was the king of Ethiopia. The apparent stationary nature of Polaris isn't truly this way. The constellation Draco is prominent in the northern sky, hurling between the pairs with a large head at one end. The Earth not only spins on its axis, it wobbles, causing the polar axis to migrate like a tiled spinning top. And the pole position presets us through a circle in the sky over the millennia to about a 26,000 year circle. In the era of the construction of the Great Pyramids, Thuban in the circle in Draco was the pole star. To have an afterlife in Egyptian cultures, a burial site needed two exits. One, a place of immortality, where a star did not appear to move, a pole star, and a second exit in the opposite direction to a place to get permission for an afterlife, or Osiris, which we now call Orion. In our polar axis' slow motion around the sky, Thuban and Osiris are no longer in the correct exit alignments. So many Egyptian spirits are wandering around the sky, lost from their burial sites for about 19,000 more years until Thuban and Osiris are back in place. These have been the Western cultural views of the northern sky. Remember that other cultures have a different impression of elements in this northern view. The second set of markers we can use is Via Galacticos, the Greek for Milky Way, leading that to the name galaxy for all such massive assemblies of stars. You can see a very light brightening as the sky moves up through Cassiopeia and north from the horizon. As we follow the winter Milky Way up from Cassiopeia, we see Camelopardalis, the giraffe, to the right of the adventurer Perseus, who beheaded the Gorgon, Medusa, by using her reflection in his shield. Since the sight of the Medusa's head would kill mortals, he carries the head with him in a bag to prove the deed was done and to use it as a weapon in times of danger. This star was known throughout the ancient Middle East as the Ghoul or Devil Star, since it is a small star circling a bigger star. This is called an eclipsing binary variable and cycles through dim and bright phases about every 2.8 days. We know it as the star Algol, the Ghoul, or the demon star. Resuming to our discussion of the Milky Way, 1 light year is equivalent to 6 trillion miles. Our home galaxy is a flat disk about 100,000 light years across, composed of flat arms. From above, it would look like a rotary lawn sprinkler. Our sun is about 1/3 of the way in towards the core in what's called the Orion spur. In our motion around the sun, due to the polar tilt, in early evening tonight, we look out at the winter Milky Way, starting at Cassiopeia and extending dimly away from the horizon across the sky. And we are looking at the outer 15% of our galaxy, the Perseus arm. Our galaxy is a disk that is brighter for us when we are placed to look inward toward the core. Moving opposite from Cassiopeia below tonight's horizon, we look inward and see the brighter intersection of the Milky Way. Tonight, the summer Milky Way will rise in the east around midnight. In early June, the summer Milky Way will be rising in early evening along the eastern horizon. From Cassiopeia in the north to the Scorpio or Scorpius Sagittarius region in the south. This is very rich in the stars of our spur and the nearby Scutum Centaurus arm, with arms separated by a dust bar called the Great Rift. Maya considered the Milky Way to be the root of the tree of life. The Seminoles see these arms and the dust band between them as the arms of the Creator protecting his creation. This is a sign to the Seminoles of the arms of the Creator protecting his creation. And if the children are afraid in the summer, they use the summer Milky Way to reassure them that they are safe. The Milky Way itself is got several interesting objects to look at. First of all, there is an interesting relationship of stars called the Summer Triangle. It starts with Vega in the constellation Lyra, or the lyre, the harp, Deneb, meaning tail, which is the tail of Cygnus the swan, and Altair, the eye of Aquila the eagle. These 3 stars can be visible in moderately bright urban areas. Just squint your eyes a bit, and that's the only 3 things you'll see. So those 3 stars are around with us, from in the early evening, starting in the early evening, probably from June until into December. Further into the Milky Way, we have the core of the area of the Milky Way. We can take a look at that. Bring it up a bit. It's around the area of Sagittarius. Now, Sagittarius, the constellation near the circle I'm drawing, Sagittarius is a centaur. He's Sagittarius the archer. And those stars along the right-hand side and the spout of what looks like a teapot are really his bow and arrow. But the Milky Way appears to be steam coming out of the teapot. And the place I've circled is our core of our galaxy with 4.5 million solar mass black hole at the center. So that's we'll be able to see that tonight, probably after midnight, but it'll get earlier and earlier as we go on into summer and fall. We've moved to our next set of markers in the sky, the ecliptic, the scientific name for the yearly path of our sun through the constellations as seen from the Earth. Because of the flat nature of our solar system, the ecliptic is also the apparent path of all the planets. Our moon's orbit is only about 5 degrees tilted from the solar system's disk. Thus, the ecliptic is the only area where Earth-viewed solar and lunar eclipses can occur. Thus, the name of the ecliptic. We are going to start following that ecliptic and look at some features. We can start with the sun that has set below the horizon about 45 minutes before this drawing was made. Next up, well, I should say below, right there is Mercury. That's the first planet that actually set right ahead of the sun. Next up is Venus. And following Venus is Uranus. Most people would not be able to see that, although if you're in a high altitude hillside, when we're on the same side as Uranus and close to it, it can actually appear in the sky. It was actually known to the Greeks, but they never noted much about it. So both Uranus and Venus are in the constellation Aries, which is just setting. Below Aries was Pisces, which set about an hour and a half, or about 45 minutes before that. Next up, we've got the constellation Taurus. That's the one that's really above the horizon. And I'll move Taurus down so we can see what Taurus has to offer. Now, Taurus is located between an asterism called the Pleiades, which are really the 7 daughters of Artemis, the goddess of the moon, if you believe the Greek legend. It's also got Orion, the constellation Orion, on the opposite side. So depending on which myth you believe, Taurus is either protecting the Pleiades from Orion the hunter, or the Taurus is the target of the hunter. But we move further up, we end up seeing Mars in Taurus. And just above Mars is the moon. The moon is very dark right now. It's only in about the 2nd day, and it will, of its illumination, and it will eventually grow from a crescent to our full moon. But if we move further up, we get to the constellation that they're in, which is Gemini, the twins. They're named after the 2 stars, Castor and Pollux. Castor happens to be on the right. They always list these alphabetically, even though Pollux comes first. Castor and Pollux are the source of the name of the constellation Gemini, or the twins. It's also got a different meaning. The separate meaning is that it's the constellation of cattle rustlers, because that was their family business, stealing livestock from other farms. In fact, that caused the loss of life of Castor. Castor was part of the distribution of the spoils from the robberies of the cattle, and he was accidentally killed in a dispute over how they'd be distributed. Next up from Gemini is Cancer. Cancer is a crab in mythology, but it's very hard to see any of the stars of Castor on normal nights in the sky. So it'll be very difficult to visit it. But right next to it is the constellation, and the sky is rotating. So as we lift our head up into the sky, we won't get astronomer's neck on this planetarium program. Stellarium. It's free, by the way, online. Just search for Stellarium. You can download this. Next, we come to the second last constellation we'll be able to see tonight. At this time, anyway, it's at 7:45. This is Leo, the lion, which is kind of redundant because Leo means lion in Greek. But it's pretty obvious when you see the backwards question mark that forms his head. He is got a special trait about him. He's the Nemean lion. He's the most armored lion in mythology. His coat will not let the penetration of any mortal weapons. Swords and spears have no effect on him. Hercules was assigned the task as one of his first 12 challenges to bring back that coat, because it was so difficult, it wasn't thought that he could accomplish it. But instead of using, when he found out his spear and his arrows wouldn't work, he strangled, using his strength. He strangled the lion and was able to use the claws of the lion to cut his coat off and take it back and prove that he had done the deed. The last constellation at 7:45 that's up is the constellation Virgo, the goddess of fertility. And in honor of that status as the goddess of fertility, the bright star you will see near the horizon at this time, looking in the east, is Spica. That means ear of wheat. So this constellation is the last one we'll see, and it is the goddess of fertility. But there is another method of finding this constellation. If you take the star Spica, you can look to the next brightest star in that constellation, Porrima, and there will be an arc of stars coming away from it. The opposite side has another arc of stars, and that makes what's called Spica and the Martini glass. So if you can see those stars, you found Virgo, the constellation. Several millennia ago in the Eastern Mediterranean, the position of the sun as it moved through constellations was used for military and municipal guidance. Later, the Greeks adopted this concept and greatly expanded it, giving us the term zodiakos kyklos, which was Greek for the motion of the sun through living objects. But that was only in ancient Greek language. In modern Greek, the word zodiakos kyklos only means a circle of animals. Zodiakos kyklos, we now call the zodiac. I've moved the scenes that we're viewing back to the western end of the ecliptic, but not part of the ecliptic, although close to it, is the constellation Orion. But I'm going to show how it's thought of in the Mayan culture. And I will use the tools here within Stellarium to actually change the culture we're looking at. We've been looking at the Western culture. Now I'm going to look at the Maya. And we'll see what the change is. We see, I'll blow this up a little bit, that what was the belt stars and the knees of Orion and the shoulders up here, this has become the primordial fire. This, the glow from the Orion Nebula made the Maya think that that was the source of the beginning of life on Earth. There are 3 stars. We call them the one at the lower left, Saïve. One knee, the other star, Rigel. The other knee, and a star called Alnitak, the top star or the left star in the belt of Orion. And so that's the primordial fire. And those 3 stars were called by the Maya the hearthstones. However, there's also 3 stars that we see as Orion's belt. And those stars right here in Mayan terminology are called the turtle. That turtle is actually those 3 stars and the turtle are the connection to the universal afterlife, before and afterlife, the rest of the universe. That's the communication path, is the turtle. In fact, in some Maya art, you will see leaders wearing turtle shells as helmets to celebrate the fact that the turtle is the center of connection to the more spiritual world. So in our view, that was a mighty hunter, but in the Mayan view, that was the source of life on Earth. I've centered our drawing back into the Western culture and in our northern view, looking back north. I wanted to point out a few other markers that we can use to navigate around the sky. The first is in the tail of the Big Dipper, or the handle, the tail of the bear, but the handle of the Big Dipper, there is a curve. And if you follow that arc down, you get to a very bright star, Arcturus. That's called the Arcta Arcturus. And the constellation Buddhist, it looks almost like a kite. Buddhist is the herdsman. He is supposed to be keeping the little bear and the big bear in the sky where they belong. It also acts as a clock. Sumerians saw the connection from Arcturus to the pale star in there as a line or as a lever they called the rudder. And so Buddhist was responsible for the rate that the sky turned. And if you turned it at the right time, sun would be in Virgo for the harvest time. And Virgo would be warm and she would be happy, and she was the goddess of fertility. So your farmers would be happy, they'd have a good crop. We can go further down in Virgo towards Spica. And we call that speeding on to Spica. When we speed on to Spica, that allows us to find Virgo. But just in case we need another way to find where the zodiac go for us, or the ecliptic, we can poke a hole in the Big Dipper. If I poke a hole in the bottom of the Big Dipper, Leo gets wet. And that's another way of finding another constellation. The important thing when studying this kind of material is to go from the known to the unknown. Most people are aware of the Big Dipper, and that's what they see. Try to expand your vision, see the whole bear. And there's a little bear here. You're likely only to, in most lighting situations, to see the bright stars at the end of the bowl of the Little Dipper, but the Little Dipper is always pouring into the Big Dipper. And if you happen to look to the opposite side of where the bear is, you've got Cassiopeia, the dark queen of Ethiopia. And that allows you to see a little more, and you can use different resources to go out and just look at the night sky and discover new things. And with that, I'd like to thank you for attending the Astronomy Festival, even if it's by electronic means. And please enjoy the rest of the evening events and get outside. Even take your kids outside if you've got a family. Look up, look at the stars, ponder what you see. And the phrase that we usually use when we're working with people with stars is, you never know what one life you'll affect, even your own. Thank you and have a nice evening.
Buddy, I'm Jim Knoll. I'm the Tucson Amateur Astronomy Association Star Party Manager, and welcome to our virtual star party. All right, so here we are with the current position of the planets, and if you look, you can kind of see Earth up here. Mercury's right in line with us and the sun, so it's actually down behind it's going to be in the glare of the sun. Venus is pretty close to the sun, so it's probably not going to be visible, very visible. Mars is right out here, and it's in good shape. It's going to be in the western sky. And as we zoom out, you can see there's Jupiter and Saturn. They'll be up pretty late. Jupiter rises. Let's see, Jupiter rises around midnight and Saturn about 11 p.m. Arizona time. So those are going to be pretty late objects. And then if we keep going out, we've got Uranus, Neptune, and then poor little Pluto out here. Pluto was demoted several years ago to a dwarf planet. And as you can see, if you compare the orbits of the other planets to Pluto, you can see that it's a little bit elongated, a little bit different. And then if we start looking at the view from the edge, then you can really see a difference between the main planets and Pluto. Most of the planets orbit in the same plane as the sun, whereas Pluto is often in a slightly different elliptical orbit. So Pluto, they think, is probably one of the larger objects, and one of the ones we've seen at the closest one for the Kuiper belt. So the Kuiper belt is just kind of a belt of leftover stuff from the solar system formation beyond Pluto. And Pluto is just one of the Kuiper belt objects. Once we get the James Webb Telescope up later this year, then hopefully they'll be able to start finding some more really cool stuff out in the Kuiper belt. So this is what the night sky looks like tonight. If you look down towards the east, pretty low in the horizon, you'll see Virgo the Maiden. This is an outline of Virgo right here. And then just above Virgo, almost straight up, but maybe slightly to the east, is Leo the Lion. Leo is actually pretty easy to find in the night sky. If you look for the bright star Regulus, it's going to be the bottom star of a backwards question mark. Just look for the backwards question mark, and that's the name of the lion. And then in this case, the body flows down towards the east, towards Virgo. And then if you look down low to the west, maybe southwest, you'll see Orion the Hunter. You'll see the three belt stars, and then you'll see the sword right down here, which is where Orion Nebula is. We'll look at that tonight as well. Looking off to the kind of north, but pretty high in the sky, is Ursa Major, or the Big Bear. That's right in here. Part of the Big Bear is the Big Dipper. Big Dipper, the handle of the Big Dipper kind of curves around or arcs around. That's part of the tail of the Big Bear. And then you've got the bucket, which is basically part of the torso of the Big Bear, Ursa Major. And the cool thing with the Big Dipper is that if you use these last two stars in the bucket, we call these the pointer stars, and they point basically towards the North Star. It'll be out here pretty much by itself. There's not a lot of other bright stuff around it. It's fairly bright, but not by any stretch of the means the brightest star in the night sky. It's not that bright. The cool thing with Polaris is that it always stays in one location because it's where the north celestial pole of the Earth points. Polaris is the last star in the handle of the Little Dipper. So you'll see it curve around here, and then here's the bucket of the Little Dipper, and it's part of Ursa Minor, or the Little Bear. Most people can generally see Polaris and probably these two end stars in the bucket. If you can see the other stars in the bucket and part of the handle, then you actually do have pretty dark skies. All right, so that's kind of what the sky looks like tonight. One of the areas that we're going to talk about tonight, in addition to objects, is we're going to talk about different kinds of galaxies. So there's basically three main types of galaxies. There's spiral galaxies, elliptical galaxies, and then what we call irregular galaxies. We'll probably look at several spiral galaxies. They're really cool because they have some very well-defined spiral arms, a nice clear nucleus in the center, very pretty to look at. They're also kind of medium-sized to somewhat large, but mostly medium-sized galaxies. They can be small to to only a few billion stars to maybe several hundred billion stars. Our Milky Way galaxy is a spiral galaxy, probably looks very similar to this, as is the Andromeda galaxy, which is the other large galaxy near us. Then we have elliptical galaxies. Elliptical galaxies, they think, are kind of the result of maybe mergers of lots of other galaxies to include spiral galaxies. And they basically just kind of get all jumbled up into a big ball. So they don't have the defined structure that you would see in a spiral galaxy, but you have just kind of a ball. They're huge. They can have upwards of trillions of stars because they've been formed by a lot of mergers of previous galaxies. The current thought right now is the Milky Way and the Andromeda galaxy would probably merge together in 4 to 5 billion years. When we do, we might form an elliptical galaxy because it'll just kind of take all the spiral arms and jumble everything up. Then we have irregular galaxies, and there's a couple of types. There's ones that are called lenticular galaxies, so they kind of stretched out. Some of them could be spiral galaxies that we're just seeing the edge on. Some of them aren't, but right in here you can see, and this is called the sombrero galaxy. It kind of looks like a sombrero hat. This would be the brim of the hat with the top and bottom part of the hat. So that's one type of galaxy, of irregular galaxy. And then another one, type 2 one, is when two galaxies collide. So when they're first starting to merge, they might stretch each other out and do some weird things to the stars and the dust and the gas. And that makes them just look kind of irregular. And this is the picture here is the antenna galaxy. And then the other thing that we're going to look a little bit at tonight is the evolution of stars. All the stars generally start with out of a cloud of cold hydrogen gas. The smaller stars, like our sun, will eventually, when they're on the main sequence, they'll last for 10 billion years on average or so. And then when they get towards the end of their life, they will start puffing off their gas, and they kind of expand out into what's called a red giant. So they'll get a lot bigger, but they're also a lot more diffuse, and the mass is still the same. They're just larger. And then eventually they'll puff off their outer gas, and that's what you see coming off of here, and that we call a planetary nebula. And then finally, what will be left will be kind of the core of the star, and that's a white dwarf. So this will be the fate of the sun in a long, long time. We don't have to worry about it for any time soon. It's going to be at least another 4 or 5 billion years, a long ways. And then the larger stars, like Betelgeuse and some of those, will become red supergiants. So they'll start off on their main sequence, but they may only last for millions of years, not billions of years. And then they become a red supergiant. So it's similar to a red giant, just much, much larger. And then finally, they will explode and become a supernova. And sometimes we can look at supernova remnants, and that's the gas that is expanded off of these red giant supergiants after they've exploded. And then they'll either become a neutron star, so they're just kind of a big, they're much, much smaller than what they were before, and they're just very dense neutrons. Or if they're really big, then they could become condensed down into a stellar mass black hole. So this isn't the super massive black holes that we have in the center of the galaxy, but these are more stellar or star-sized black holes. So we'll see some of those kinds of objects probably over tonight as well. All right, the last thing I want to briefly mention before we get into doing some observing is a little bit on astronomy terms. Throughout the program, you'll hear us refer to object as a Messier or M number. Those are objects that were recorded by Charles Messier back in the 1700s as he was looking for comets. And he noticed these things didn't move, but they kind of looked like comets because they were fuzzy. And so he chose to record them so that he wouldn't confuse them with future observations. And they've now become some of the best objects for amateurs to view. Well, also another large catalog that we use is the New General Catalog, or NGC. So you'll hear us refer to NGC numbers as well. You will talk a little bit about magnitudes. The lower the number, the brighter the object. Normally a magnitude 6 or a little lower than that, maybe a 5 is naked eye. So that means it's something you can see with your naked eye. If it's a higher number than 6, then you probably need a telescope or binoculars. And then finally, a light year. Light year is a distance that light travels in 1 year. So at 186,000 miles per second, that's about 6 trillion miles per year, or about 9.5 trillion kilometers. It's so we use this to measure distance between objects. Now what we're going to do is take a look at some of the astronomers' equipment. We'll start off with Jim O'Connor. Jim.
Thanks, Jim. What you're seeing in front of there is exactly where I'm sitting right now, except it's nicely a bit darker. My equipment starts out with a 10-inch Schmidt-Cassegrain telescope. But rather than using an eyepiece in it, I've put a video camera on the back end. That telescope, and you can see it farther away on the left and up close and personal on the right. It's a very old one. It's almost 30 years old, so I've got a rather newer mount it's on, the thing that holds it up and lets it move around the sky. It's a Celestron AVX equatorial mount. So it's a 10-inch Schmidt-Cassegrain telescope on an equatorial mount. The camera is called a Mellencamp Terminator. It's got a high sensitivity CCD. It's one of the highest sensitivity video chips in the world, but it's small. It's only 1/4 of an inch on a side, that chip. So it's only got 377,000 pixels. So it does not give you a whole lot of grabbing of light, but it can go a long way away and grab it. It's in full color, and it's got a thermoelectric cooler on the inside. And that's what if you look closely at the camera, you see these big fans on the outside. That's keeping it cool. But that whole setup is what I use when I go out and show things. And if you look in the left-hand picture, there is a monitor on a stand. That monitor is what I use for public viewing, because more people can see what I'm looking at, and then I know what they're seeing. Jim?
Okay, thank you. And now over to Rick.
You'll see that my scope is of a different design than Jim's. Mine is a refractor telescope, uses lenses rather than mirrors. It's a 4-inch stellar view refractor on a very large Losmandy G11 mount. Gives me very good stability for imaging. And I'm running an ASI 2600 color cooled camera. The sensor inside this camera has been specially adapted for this service, but it's very similar to what you would find inside a modern digital SLR camera.
All right, thanks, Rick. And Bernie?
Hi, everyone. I'm Bernie Stinger. I'm presently out at our dark sky site in the Chiricahua Mountains, about 100 miles southeast of Tucson. And at that site, we have several permanent paired telescopes. One of them is the one I'll be using this evening, which is a 9-inch folded refractor. And it's mounted onto this heavy-duty astrophysics mount. Now, all of the camera control and everything is coming back that big black wire on the left side back into the control room, which is the white building in the upper left corner. And that's where I'm sitting right now, controlling the camera and what we'll be looking at this evening. The camera I'm using is a Malincam DS432C. It's a color camera, it's a CMOS camera, and it's very sensitive to light. Some of the objects we'll be looking at tonight are very, very faint. So I'm using my most sensitive camera. Back to you, Jim.
All right, so that's kind of just a quick overview of the equipment. So now let's get on to some deep sky observing.
My first object tonight is called the Medusa Nebula. It's a planetary nebula up in the constellation Gemini. It's also goes by the name of APN 205.1 plus 14.2. I know that's an exciting name. That's why they use Medusa Nebula instead. This is a very, very faint object. It's not something that I would recommend the beginning amateur to try to look for in a telescope because of its very, very low surface brightness. But if you do get a camera and you want to give it a shot, it is in Gemini, and it shouldn't be too hard to find. This was discovered in 1955 by George Abel. Now, the date 1955 kind of gives you an idea of how faint it is, because for something to be discovered that late into the 20th century means it was missed by many, many people for many, many years. Most objects like this, at least planetaries, were discovered in the 17th and 18th century, or the 18th and 19th century, not up until the 20th century. And it goes by the name of Abel 21 as well. That's another name for it. It's 1,500 light years away, so it's relatively close. And it's about 4 light years wide. So if you go from the top of the reddish area there down to the bottom, you're talking about 4 light years. Now, this is a planetary nebula, which means that it was formed by an exploding star. When that star exploded, it threw off a shell of gas, its outer atmosphere. And we know it was hydrogen because it's mostly red. These red streaks in here are ionized hydrogen, and they're being ionized by the parent star or stars in the general area. The actual parent star has never actually been determined. It could be any one of these. It's very hard to track it back unless it exploded again and you could catch it. It's called the Medusa Nebula because it kind of looks like a hairdo, and these streaks in here, someone or several people felt it reminded them of the head of Medusa and the snakes coming off of the hairdo of the head of Medusa. So that's why it's called the Medusa Nebula.
So what we're looking at here is known as the Orion Nebula. This nebula is located in the Orion constellation. For those of you familiar with the Orion constellation, most people are familiar with this belt going across the three sides of his belt. This is located below his belt in his sword. This object is actually visible with just a pair of binoculars. If you were to look up when Orion's up in the sky with a pair of binoculars, you should be able to see the Orion Nebula if you know right where to look. This is one of the brightest nebulas in our sky. You are seeing it with your naked eye when you look up there. You could see the brightness from it. It's also one of the closest nebulas to the Earth, and it's an active star forming region. That center core brightness you're seeing is because there's several bright young stars in there, and there's new stars being made inside this cloud. The nebula is so close to Earth that it's actively studied by astronomers because it is so large and so close. It's an easy star forming region to study. So to give you an idea of its size and its closeness, it's about 1,400 light years away, which in stellar terms is not that far away. And it's about 34 light years across. So you're talking about a very, very large structure. Now, right next to him over to the right is actually a separate little nebula known as the Running Man. And from your perspective, he's upside down right now. His head is towards the bottom. He's got two little arms sticking out and his legs sticking up. That's the little Running Man Nebula. Both of these are part of the Orion complex. There is nebulous gas running all up the left side of Orion, and there's several other nebulas north of this, above this. So that is the Orion Nebula.
Yeah, and if you remember, from any previous discussions, whatnot, so like Rick mentioned, that's a stellar nursery. So stars are being born in there, and it'll produce hundreds, if not thousands, of stars. Very gorgeous picture, Rick. Thanks.
Hi, I'm Jim, the last of the guys showing off interesting things here. And what we're looking at is an open cluster whose number in the catalog is NGC 188, or sometimes called Caldwell 1. But its name is the Polarissima cluster. And the reason that it's called Polarissima is there are many objects in catalogs that have the name Polarissima. It means they're next to a pole of some kind. In this case, it's an open cluster that's near the pole of the Milky Way galaxy as we look up. The Polarissima cluster is an open cluster about 23 light years in diameter. It's in the constellation Cepheus. So that means that sometimes it can be awfully low in the sky, or sometimes a lot higher in the sky, but it's only 5 degrees away from our pole star in the sky. It's unlike most open clusters that drift apart after a few million years because of the gravitational interaction with the Milky Way. NGC 188 lies far above the plane of the Milky Way. It is one of the most ancient of open clusters known. It's further away from our galaxy's center than our sun is, and its age is approximately 6.8 billion years. So its star's mass is holding this thing together. NGC 188 is about 5,000 light years away from Earth, which puts it above the Milky Way's disk and further from the center of the galaxy than the sun.
This object filling the screen is the Rosette Nebula. It's a large circular emission nebula located in the constellation Monoceros. It surrounds a cluster of young hot stars known as the Rosette cluster. You can see them there in the center. There's kind of a hole in the middle of this nebula. The cluster itself was discovered quite a while ago, back in 1690. It was recognized as a cluster. The nebula itself wasn't discovered until quite later. It's quite dim, even in a visual telescope. It requires photographic techniques to be able to pull out that nebulosity. The nebula itself is large. It covers an area in our sky about 5 times the size of the full moon. So it's a very, very large object. It's one of the most photographed objects. It's really one of the most pretty and detailed nebulas up there. So the reason it's red, it's dominantly red, that's because of the hydrogen gas, and that is the color that hydrogen gas puts out when it's being excited in an emission nebula like this, when there's energy behind it. The total diameter of what you're seeing there is about 130 light years across, and that central hole is about 30 light years across. So the reason that there's a hole in the center there is that the group of stars that are there in the middle have created stellar wind. They put out radiation, and that radiation is called a stellar wind. And that wind has swept out that central core, and that's why we have that hole that's there. But this is another a nebula that is an active star forming region. That the gases in there are coalescing and condensing down into forming new stars.
The object in front of you is Messier object number 1. Charles Messier was a employee of the French Navy. He was assigned to be the chronicler of dynamic events. So he spent his career with the French Navy looking for comets. When he would find something that wasn't a comet but might fool someone, he noted it down. This is the very first one he found. It's called Messier number 1, or the Crab Nebula. It's in the constellation Taurus, and it's the remains of a star that was at least 8 times as big as our sun. What happened is it used up all its hydrogen and started making more elements. And as it started going through stages of making more and more elements, it got to be a red giant. And then, unfortunately, when it got to making silicon and iron, when it started making those, the debris from them, or the byproducts of them, sucked all the energy out of the other layers of the star, and it collapsed on itself in about 10 seconds. Usually when a star that's that large starts to make iron, the star has about 10 seconds or so to live. So it blows itself apart catastrophically in a nuclear explosion that creates a lot of the materials that we need for life. This object right here is ran out of its hydrogen and collapsed, and the entire nebula is about 5.5 light years across. At the center of it is the remains of the star. There was some debris left over, and it's small. It's about the size of a small city. And the common name comes from William Parsons, the 3rd Earl of Rosse, who observed the object in 1840 using a 36-inch telescope and produced a drawing that looked like a crab. We know when it happened because it was documented both in China and in the United States. It happened in 1054 on July the 4th. The Chinese, who were prolific star viewers, star observers, were looking for what they called visiting stars. And they saw this event happen. The next morning, July the 5th, it was noticed by the populations around what's called in the United States, the Four Corners area, the Anasazi culture, the area around White Canyon, Navajo Canyon, and in Chaco Canyon. And we can know about it because it was sketched and left as a glyph or a hieroglyph on walls and cave paintings and cave art, because it shows that as an exploded star, because they saw it in the daytime and it looked like a bright sun, but very small. And so what they did was they put next to it what they saw as far as the moon at the time, a crescent moon, only a few fingers away in the drawings. And it turns out that the moon, crescent moon, was only about a half a degree away in the sky when that happened. So the Native American cultures around in northern New Mexico and Arizona, and the Chinese were the people who documented this, and we know very precisely that it happened in the year 1054 on July the 4th.
Okay, my next object is one of my very favorites. It's a edge-on galaxy in Coma Berenices. It goes by the name of NGC 4565. Unfortunately, it doesn't have a common name, but it's a beautiful edge-on. One of the beautiful parts of this galaxy is not only is it edge-on, but there's a beautiful dust lane that runs down right down the center of it. And the orientation of the galaxy is not exactly at 90 degrees to us. It's just tilted ever so slightly forward. So we can see this side of it in my image here, the left top side of it, a little better than the bottom side. And you can see very faintly that there appears to be spiral arms spiraling around this galaxy. And also the central core of the galaxy, where most of the stars are, is very, very bright on the top, but not so bright on the bottom, which also gives you the distinct impression that we're looking at it ever so slightly tilted towards us. This is 40 million light years distant, so it's far, far beyond our galaxy. It was discovered in 1785 by William Herschel in the late 1700s. It's in the Coma group of galaxies. So we have a local group of galaxies, and then we have groups of galaxies that are nearby us, but not part of our local group. This is part of the Coma group of galaxies, which is fairly close by, being 40 million light years. This is thought to be a barred spiral, so there may be a bar of light or star formation right down the center, but it's really hard to tell from the angle of view that we have available to us. This one should be visible in smaller telescopes. If you want to take a look, try to spot it. If you have a go-to scope, plug in NGC 4565 and have fun. My next object is M87. It's also known as NGC 4486. This is a supergiant elliptical galaxy in the constellation Virgo. So this fuzzy patch right in the center here is not a star, it's a galaxy. However, unlike many galaxies that we show you on these video presentations, it doesn't have spiral arms. It looks more like a great big fuzzball. And that's why, one of the reasons why they call it an elliptical galaxy, because it has no distinct shape. There's about 1 trillion stars in this galaxy. So it's an enormous supergiant galaxy. It was discovered in 1781 by Charles Messier. And of course, he put it on his list of things that aren't comets. So it's number 87 on his list. It's also known as the Smoking Gun Galaxy. And I'll explain why a little further on. It's 53 million light years distant. At the center, well, not exactly at the center, but near the edge of the galaxy, they discovered many years ago a bright radio source. And they were trying to figure out where that radio source was coming from. It seemed like it was coming from not so much the center as it was coming from the edge of the galaxy. And they were finally able to zero in on it. And that radio source turned out to be a jet of superheated plasma that was being shot out from the center of the galaxy. And it was being thrown out over 5,000 light years from the center. Because of that, it was quite obviously coming from a supermassive black hole at the center of the galaxy. And that supermassive black hole has approximately 6.5 billion suns inside it. In other words, over the lifetime of that galaxy, that black hole is swallowed up 6.5 billion suns. Now, why do they call it a smoking gun? Because that jet is visible under just the right conditions. And tonight, it's visible. So if we zoom in on the galaxy, you can actually see that jet of gas that's shooting out of the galaxy itself, some 5,000 light years out into space. And that is from the supermassive black hole. That black hole is spinning like a top, and from the top and the bottom of that spinning black hole is this super hot plasma that's being shot out. Now, they've looked for it going the other way. It hasn't been detected in the other direction, but it certainly has been, certainly can be seen in this direction. Now, those of you who've been maybe watching scientific events will have noticed back in 2019 that they published the first image of a black hole. And that is the black hole from the center of this galaxy. And that black hole that they imaged is what's squirting this hot plasma jet out into space. So that's why they call it the smoking gun galaxy. Yeah, the jet is readily apparent even at low magnification. In the upper left here is another galaxy, and you'll notice on that one there's no jet on that one, just on M87. So it's very obvious that's M87 just from that spike, that plasma jet being shot out of it.
This object has got a new general catalog number, NGC 2360, but it also has a name as Caroline's cluster. One of the new age of astronomers that really brought astronomy forward and got to be much more discoveries made was William Herschel. But he actually was an orchestra conductor. And he had heard that making a parabolic mirror for a telescope If he looked at the light reflection patterns from it, it would have an order that was like chords of music. So that he could be a better composer and an orchestra conductor, he started making telescopes. And he spent the rest of his career doing two things, one being the conductor of the Bath Symphony Orchestra in England, and the other was building 400 telescopes for himself and for other people. He ended up, because of his accomplishments, being given a residence at Buckingham Palace, working with King George III as his personal astronomer. But what this object is, the reason it's called Caroline's cluster, is it was his sister who discovered this. His sister he brought over from Austria because he needed a singer in the orchestra. But she was watching his astronomy and kept correcting his math. So she sent her to Oxford, where she got all the possible mathematics that were available in that era. And she became one of the most profound mathematicians as well as astronomers of the time. She found 11 comets on her own, and she actually was awarded a gold medal from what had become Prussia when the countries had kept changing their boundaries. But the King of Prussia awarded her a gold medal as the person from Prussia who had accomplished the most notable achievement in the world. She was 92 years old when she was awarded that. She actually traveled from England to Prussia to accept it. She lived to be 96 years old, and she was an astronomer for 72 of those years. This is a cluster she found in Canis Major. That's a dog cluster. It's got the dog star, Sirius, and one reason it's called the dog star is that just happened. Oh, that's why summer in August is called the dog days of summer. Is that's when the sun happens to go through that area. So this cluster was discovered by Caroline on 26th of February in 1783. And she described it as a beautiful cluster of pretty compressed stars near a half a degree in diameter. Now, half a degree is a full moon. Her notes were overlooked until her brother William included her cluster in a 1786 catalog of 1,000 clusters and nebulae, and he acknowledged her as the discoverer. The age of this cluster, 2.2 billion years old. That's very old for an open cluster. Normally, the galactic momentum, the spin of the galaxy, and the gravity of the stars around it that make up the galaxy will pull clusters apart eventually. But this one is held together for 2.2 billion years. Its diameter is about 15 light years across, and it's 3,700 light years from Earth. But there is Caroline's cluster.
So in this picture, we're not looking at one single object. We're looking at close to 20. Everything you're seeing in this image that is not close to a pinpoint of light is a galaxy. This is known as Markarian's chain. It makes a little chain of galaxies, but every little smudge of light you see here is a galaxy. There's a galaxy up here. There's one down here. There's 3 or 4 down here. There's a couple faint ones there. The bright one here is known as Messier 86. Messier saw this object, and he cataloged it. This is a known as a lenticular galaxy. That's its shape. On either side of it here, we have a couple spiral galaxies that we're seeing edge on, another lenticular galaxy up here. And then down here, these two galaxies are companions. They're known as the Eyes galaxies. They are intertwined with each other, and they're so close that they've warped each other. If you look at the lower one here, you can see some wispy structure kind of curving around it. The little companion here has caused that disruption. They've been swirling around each other and distorting their shape. they were first discovered in the 19th century. They've been known for quite a while. These galaxies are all located up in the Virgo constellation. It's known as the Virgo supercluster of galaxies. And although you're seeing a lot of galaxies in this image frame, if I were to reorient my telescope to the left, to the right, up or down, we'd get more galaxies. There are hundreds of galaxies in this region of space. One reason we can see so many galaxies is when we're looking up at Virgo at this time of year, we're actually pointed outside the plane of our galaxy, of our own galaxy. So we're looking more out into space, deeper space, and we can see all these galaxies. They're all at varying distances. The ICE galaxies are about 37 million light years away. The larger one is about 98,000 light years across, which is a fairly large galaxy.
Now we're going to move on to another galaxy. This galaxy is M91. M91 is in the constellation Coma Berenices. And the unusual thing about, not particularly unusual per se, but the nice thing about M91 is it's a barred spiral that's face on. So in the event that you don't know what a barred spiral is, here's an excellent example of what a barred spiral looks like. You can clearly see the central bulge. It has almost a stellar-like central bulge, but it has a bar across of stars, and then the arms radiate or appear to radiate from the ends of the bars. So they radiate out in a nice, beautiful spiraling pattern. And that's what gives it the name barred spiral. M91 was discovered by, again, Charles Messier in 1781. As we talked about earlier, Messier spent a long time looking for comets, and this certainly would have caught his attention. The galaxy is 63 million light years distance, so it's definitely more distant than some of the other galaxies that we've looked at this evening. And this particular galaxy has a what's called a low star formation, meaning that the stars that are in the galaxy at the present time have been there for a long time, and the galaxy is not creating new stars, or if it is, they're at a very, very low rate. Now, there's several reasons why that could be. One reason, or one possible reason, is that there is very little collision of gas and stars within the galaxy arms itself. And another possible reason is that the galaxy has not collided with another galaxy and caused star formation for that reason. Star formation usually happens when there's collisions, either internally or from other galaxies colliding with a galaxy. And this one appears to be kind of on its own out there in space. There's a very, very small galaxy to the right of it, lower right of it, but I suspect because of its size, that's very, very distant. And if we back off, here's another galaxy off in the distance, but again, that's probably at a very
very long or distant from from M91. So it's probably not affecting it to any significant degree.
This object is Messier 37, also known as the salt and pepper cluster. It's an open star cluster. It's considered to be one of the finest in the sky. For an open cluster, it's actually still fairly dense. The cluster was first discovered by Giovanni Battista Hedderna around 1654, but Hedderna's observations were unknown until his writings were found in 1984. So long, long after his discovery was it discovered that he had found it first. There's two other companion star clusters in this area, M36 and M38. They were both discovered by Lee Gentile, but he missed this one. He did not find M37. So it was independently discovered by Charles Messier, who found it in 1764. It contains about 150 primary stars with magnitudes of 9 to 12.5. Total membership is probably around 500 stars. It covers an area nearly as large as the full moon. It's a very large cluster. And it includes a bright orange star you can see off to the left there. There's a very bright orange star. That's actually part of this cluster. So this cluster extends out beyond the bright core there. It's about 4,600 light years away, and it's got a total diameter of about 25 light years. It also is an older cluster. It does contain at least a dozen red giant stars within it, which are stars which are larger and getting towards the end of their lives.
Open clusters are also really cool to look at in small telescopes. So if you have a small telescope or even binoculars, pull it out and try to find some of these objects. You can go to a lot of online sources or apps to find out where they're at. And as Rick said, this is M37. So you just would put in M37 in your app or planetarium program, and the program I used, the planetarium program will be able to show you where it's at in the night sky and try to find them.
And there's many free planetarium programs available for phones. If you go look on Android and Apple stores, you'll find several good free apps that can help you locate these objects.
The object you see in front of you is Messier's object number 82. It's in Ursa Major, a big bear, and it's coming up pretty high in the sky right now. M82 is called a starburst galaxy. That's why you see all the glowing in there. There are giant stars, millions of them being formed right now. The reason you see a cut down the middle of it is dust from the initial ignition of the nuclear reactions on the stars that are formed. You may be able to see some shadowy shading on both ends. Those are billions of more stars that are already formed. In the middle, towards the core of the galaxy, there are such tremendously large and tremendous number of stars being formed that is quite a it's quite an object to see in a telescope, even looking at it. There's at least there's spiral arms have been found, so you can see a spiral arm around the left side, upper left side, that's coming around the outside of the galaxy. Most of the action is in the near the middle. It's got two supermassive black holes in the center, and nearly 200 massive clusters of around 200,000 stars each are in those bright blobs. So that is a rather interesting massive star-forming galaxy that is fairly close to us. and about 12 million light years away. And it's an object that allows us to study star formation and galactic behavior. But the fascinating thing about it is not only is a starburst, in fact, it's got two supermassive black holes. Our next object is galaxy M108. It's one of the last objects in the Messier catalog. The Messier catalog has 110 objects in it, and this is number 108. This is a galaxy in Ursa Major, so it's up near the Big Dipper. This is a barred spiral galaxy that we're looking at almost edge on. It's inclined at about 75 degrees, according to the textbooks. It was discovered in 1781. So obviously one of Messier's finds, and given a later number in his catalog. At the center of this galaxy is another black hole. This one has what's called an intermediate mass black hole. Now, that's a little different from what most galaxies have. There are black holes, stars that have collapsed into black holes, or a single black hole. And then there are supermassive black holes where the center of galaxies have black holes that have millions or even billions of suns involved. And then there are intermediate mass black holes. These are more rare, and they are involved, they have levels of thousands or maybe hundreds of thousands of solar masses. This galaxy also has some nice structure to it. You can see the knots in the arms of the galaxy. These bright knots typically indicate what's called H2 regions, which are hot hydrogen regions within the arms where new stars are being formed. And because those new stars are being formed, there's a lot of light output from those new stars. So this is M108 in Ursa Major. And while I was imaging this particular galaxy, I noticed down below, within the same field of view, over in the lower right is another object. This is a foreground object. This is an object within our own galaxy, whereas this is another galaxy. This is an object within our own galaxy, and this is called a planetary nebula. These are planets, these are stars that have exploded and blown off the outer shells of their atmospheres out into space. And this particular one is called the Owl Nebula. It's a planetary nebula, and the star that has formed this nebula is right there in the center. That's the star that formed formed this nebula. And the reason they call it an Owl Nebula is because of the two black patches that look like eyeballs in the night, with a white spot, the center star, looking like a little nose. So it looks like an owl's face in the night, and that's the reason why it's called the Owl Planetary Nebula.
All right, we're now looking at another galaxy. This is called M109. It's one of the latter ones in Charles Messier's object list. It's a barred spiral galaxy, so you can see the bar kind of going diagonally through the galaxy, and you can see just a really gorgeous view of the spiral arms, pretty much wrapping around the galaxy. This is a fairly tightly wound galaxy. It's also quite far away from us. It's about 82 million light years away, so it is way out there. It is in the constellation of Ursa Major. It was, you can kind of see it it's very close to one of the bowl stars of the Big Dipper. So if you've got a pair of binoculars, you might even be able to pull it in with a decent pair of binoculars. So it's going to be right next to the bottom star, which is that bright star that's coming into view now, of the bottom end of the bowl of the Big Dipper on towards the handle end. So it's a very, very classic barred spiral galaxy.
Okay, we've had a successful star party. I hope you've been able to see some of the nice deep sky objects in our nice dark skies. And earlier we had the solar observing, and we've had lots of activities all throughout the Astronomy Festival. We've been doing these outreach events for well over 20 years. And since 2014, we've been doing the Astronomy Festival in April or around April since 2014 at Brandy Fenton Park. Next year, we're hoping to be back in person at Brandy Fenton Park. Tentatively, the date will be April 9th, 2022. You can watch our website, our Facebook page. It's a little too early right now to know what we're going to be doing in April, but watch our website and our Facebook page to find out when that event will be. We also have other activities throughout the year. We've got star parties at parks and such, open to the public events. So watch our website, our Facebook page. All of the recordings from today's activities and observing sessions will be available online later. Feel free to share them with your family and friends. And I thank you for coming. May?
Thanks for sharing our event with us today. We love people to join us and share with us the wonderfulness of the sky and learning about the sky. Please to follow up on this and do more of this, check out our website at tucsonastronomy.org, and it will list our upcoming virtual and in-person events and activities of the club. We hope that you at some point can join us for our monthly meeting, the first Friday of every month at 6:30. It streams live on Facebook, and we have lots of interesting astronomy topics and activities. And please contact us in the future anytime you wish.
All right, and I will echo the thanks that Terry and May provided. Hopefully you enjoyed what we did. We enjoyed putting all these activities on. As we mentioned earlier, it's never as good as being in person, but I think you'll hopefully will enjoy what we've put together for you. All of our previous events, as Terry mentioned, and our virtual star parties are all on our YouTube channel and on the Facebook page. So again, check those out for if you want to watch any of those, as will this will be on there as well. And if you're in the Tucson area, we're starting to do a few in-person events now, some public ones. We really hope we'll be back in earnest in the fall. So just watch the website and Facebook for upcoming events. I'm going to put up a couple of slides that have some links to different events and organizations that we've talked about throughout the festival. So feel free to, you can either take a picture of them or stop the recording at that point in time and click on them so that you can get additional information. Other than that, hopefully you enjoyed everything. Think clear skies and dark skies and keep looking up. See you next year.